150 million years ago, Earth was still in the age of giants. The late Jurassic world was filled with towering sauropods, swift predators, and warm shallow seas, crowded with coiled ammonites and marine reptiles. But about 145 million years ago, long before the famous asteroid at the end of the Cretaceous, this thriving planet entered a quieter crisis. The Jurassic did not end with a single impact. It faded out. When most people imagine the end of the dinosaurs, they picture a blinding flash, global firestorms, and a crater cut into the crust of the planet. Yet there was an earlier turning point that left no obvious scar on the surface, no single crater, no soot layer wrapped around Earth, and almost no space in textbooks. How could an extinction event that reshaped dinosaur and marine ecosystems leave behind only scattered clues in limestone cliffs and deep-sea sediments? Scientists now focus on the interval spanning the latest Jurassic and earliest Cretaceous, known as the Tithonian Berriasian. During this time, many familiar organisms began to slip away. Ammonites that had dominated the oceans for tens of millions of years started to vanish in wave after wave of losses. Coral reefs struggled, with major reef builders declining or disappearing in several regions. Large marine reptiles that once ruled the seas became less diverse, while on land, certain dinosaur lineages faded and new groups slowly took their place. This was not a single catastrophic day. It was a drawn-out transition recorded layer by layer in rock. Over time, diversity curves, isotope measurements, and fossil ranges show a pattern of stress and replacement rather than sudden annihilation. Because of this drawn-out character, the end Jurassic crisis often appears more like background change than a dramatic boundary. Yet its long-term impact on life was profound. All of this unfolded while the supercontinent Pangaea was breaking apart. Earlier in Earth's history, most continents had been joined into this vast landmass. By the late Jurassic, rifts had opened, new ocean crust was being formed, and the first branches of the Atlantic Ocean were widening. This process rearranged ocean gateways, altered currents, and changed how heat and moisture moved around the planet. As a result, climates shifted, coastlines reorganized, and habitats that once seemed stable were gradually rewired. Hidden in these slow changes is the mystery at the heart of this story. What combination of volcanic activity, greenhouse warming, ocean anoxia, and ecological competition turned the end of the Jurassic into a geological whisper rather than a shout? How can a crisis that nearly reset life in the seas be traced only through subtle chemical signals and fading fossil lineages? The journey ahead follows Earth from its early supercontinent history into the rise and breakup of Pangaea, then into the environmental upheavals that shaped the Tithonian Berriasian world. It will explore how researchers read the rocks, reconstruct vanished oceans, and piece together an extinction that changed the direction of life without ever announcing itself with a single catastrophic blow. In popular imagination, the age of dinosaurs ends with a single moment: an asteroid, a crater, and a sudden global winter. Yet tens of millions of years earlier, the Jurassic world had already passed through a quieter crisis. During this time, dinosaurs did not vanish. Instead, their world was stripped down and rebuilt around them. To understand why this matters, it helps to compare these two endings. The Cretaceous-Paleogene event is dramatic, short, and obvious in the rock record. The end Jurassic interval, by contrast, stretches across several million years at the Tithonian Berriasian boundary. Extinction rates rose, ecosystems faltered, and long-established lineages faded. But there was no single day when everything changed. Over time, this process reshaped who dominated the land and, even more strikingly, who dominated the seas. Late Jurassic oceans represent one of the high points of marine biodiversity in Earth's history. Warm epicontinental seas spread across the margins of the continents. Ammonites and belemnites filled the water column, forming dense tiers of shelled predators and scavengers. Coral and sponge reef builders constructed complex habitats on shallow platforms. Above them, large marine reptiles such as pliosaurs and early plesiosaurs ruled the open ocean, while ichthyosaurs still occupied fast-swimming roles. When this system began to erode, it was not a minor adjustment. It was a direct challenge to the structure of marine food webs. Yet this episode is not counted among the classic Big Five mass extinctions. That absence raises an important question. Where is the boundary between background extinction and a true global crisis? Paleontologists measure diversity curves, extinction intensities, and ecological disruption, and the end Jurassic sites in a gray zone. It does not reach the devastating intensity of the end Permian or end Cretaceous, but it surpasses ordinary turnover in several groups. Because of this, it forces scientists to reconsider whether the traditional list of mass extinctions captures the full range of planetary upheavals. Part of the challenge lies in the nature of the event itself. Instead of a single catastrophic trigger, the end Jurassic appears to reflect a drawn-out combination of tectonics and climate change. As Pangaea continued to fragment, new ocean basins opened, seaways rearranged, and sea levels shifted across continental shelves. Large volcanic provinces released heat and greenhouse gases, driving episodes of warming. In many basins, black shales rich in organic matter indicate expanding zones of ocean anoxia, where bottom waters lost oxygen and benthic communities collapsed. This quiet extinction unfolded as a sequence of stresses that gradually wore down resilience rather than removing it in an instant. For dinosaurs on land, survival did not mean stasis. Certain Jurassic lineages, including some long-necked sauropods and early theropod groups, declined or disappeared, while more derived clades that would dominate the Cretaceous expanded into the ecological space left behind. In the oceans, new types of plesiosaurs and later mosasaurs would eventually exploit niches opened by the loss of older marine reptiles and invertebrates. As a result, the Cretaceous world inherited reorganized food webs, altered climate patterns, and different continental outlines than those of the classic Jurassic scenes. In this sense, the quiet end of the Jurassic acted as a hidden prelude to the better-known catastrophe at the end of the Cretaceous. It set the stage on which later events would play out. How can this subtle restructuring be detected in rocks and fossils that seem, at first glance, continuous and undisturbed? The next section turns to the evidence that reveals a global crisis hiding in plain sight. To understand that hidden crisis, the story must step back to the largest stage Earth has ever built for life, the supercontinent Pangaea. During the late Paleozoic and early Mesozoic, nearly all major continents were welded together into one vast landmass, surrounded by a single global ocean. This arrangement was not just a different map, it was a different planetary system. Pangaea did not appear suddenly. During its earliest history, the planet's plates carried older continents, such as Laurentia, Gondwana, and Baltica, toward one another. Long mountain belts formed as these blocks collided, crumpling the crust and thickening it like a geological scar. Over time, this process assembled a supercontinent that stretched almost from pole to pole, with an interior so broad that some regions lay thousands of kilometers from any sea. Such a supercontinent changed climate in fundamental ways. With so much land joined together, moist oceanic air could not easily reach the continental interior. As a result, vast desert regions developed, while seasonal heating created strong monsoonal wind patterns around the margins. The global ocean that surrounded Pangaea had relatively few broad, shallow continental shelves, limiting the productive coastal habitats that many marine organisms prefer. Life in the early Mesozoic evolved under these conditions, adapting to extreme interiors, strongly seasonal climates, and long, relatively simple coastlines. Yet Pangaea was not stable. Heat rising from the mantle gradually weakened parts of the thickened crust. During this time, great rift systems opened as the supercontinent began to split. By the late Triassic, cracks stretched between what would become North America Africa, and Europe. In the early Jurassic, these rifts deepened and filled with lava and sediments, marking the first stages of the Central Atlantic opening. As the Jurassic progressed, those rifts linked together and allowed new oceanic crust to form. The Central Atlantic Ocean began as a narrow seaway, then widened as plates continued to move apart. Because of this, coastlines lengthened, new shallow seas appeared, and ocean gateways between regions opened and closed. Changing connections between basins altered currents, temperatures, and the distribution of nutrients in the water. These tectonic shifts quietly rewired Earth's climate and oceans. Ocean circulation patterns that had been stable for tens of millions of years became more complex. Regional climates changed as fresh coastlines redirected winds and moisture. Some marine ecosystems thrived in new shallow shelves, while others declined as their preferred environments disappeared. On land, shifting positions of the continents influenced rainfall belts and vegetation zones, gradually reshaping habitats for dinosaurs and other animals. By the close of the Jurassic, Pangaea had already moved far from its peak configuration. The supercontinent's breakup had introduced new seaways, restructured currents, and altered climate gradients across the planet. No single impact or sudden catastrophe marked this transformation. Yet the cumulative changes pushed many species toward ecological limits. What traces did this slow tectonic reorganization leave in the rocks? And how did it translate into a quiet wave of extinction rather than a single dramatic event? The next part of the story follows that trail of evidence, from isotope curves to vanished reef communities, to reveal how a shattering supercontinent helped close the Jurassic world. To follow that quiet wave of extinction back to its source, the story has to be widened. The end of the Jurassic is only understandable when set against a deeper reality. Earth's surface never truly rests. Continents, oceans, and mountain belts are temporary expressions of motions that began when the planet itself first formed. During its earliest history, Earth looked nothing like the world familiar today. Soon after formation, intense impacts from asteroids and comets delivered energy faster than the young planet could lose it. Because of this, much of the outer layer melted. Instead of a stable crust, the surface was dominated by a global or near-global magma ocean, with no permanent continents and no long-lived oceans to moderate climate. As the planet slowly radiated heat into space, this molten shell began to cool and harden. A thin, fragile crust formed on top of the still hot mantle. Large impacts repeatedly broke this early crust apart, allowing fresh magma to rise, spread, and solidify again. Over time, this process created small, buoyant fragments that were slightly richer in lighter elements, such as silica. These early continental seeds, called cratons, were the first pieces of land capable of surviving for billions of years. At the same time, volcanic eruptions released vast quantities of water vapor, carbon dioxide, and other gases, building an early atmosphere very different from the present one. When the surface cooled enough, water condensed, clouds thickened, and long-lasting rains began to fall. Rainwater collected in low areas of the crust and formed the first persistent oceans. During this time, interactions between rock, ocean, and atmosphere started to regulate temperature and chemistry on a planetary scale. Beneath this evolving surface, slow motions in the mantle organized into convection cells that carried heat from the deep interior toward the crust. The rigid outer shell fractured into plates that moved, collided, and sank back into the mantle. Plate tectonics became the engine that assembled and destroyed oceans and continents. Mid-ocean ridges, subduction zones, and great fault systems were all expressions of the same underlying drive to move heat outward. This constant rearrangement led to a repeating pattern in Earth's history, the supercontinent cycle. Over hundreds of millions of years, scattered continents drifted together, collided to form enormous landmasses, then eventually rifted apart again. Earlier supercontinents, such as Columbia and Rodinia, altered ocean circulation, mountain building, and climate, and as a result, they reshaped the evolution of life long before Pangaea existed. Here is the unexpected connection. Every quiet shoreline in the late Jurassic, every reef platform and shallow seaway was positioned by this deep, slow machinery. The breakup of Pangaea, the opening of new ocean basins, and the subtle environmental stresses that ended the Jurassic were late chapters in a story that began with magma oceans, mantle convection, and the first unstable crust. The next step is to see how this long supercontinent cycle set the exact stage on which the Jurassic world would finally falter. By the time Pangaea came together, Earth was not trying something new. It was repeating an old experiment. Long before the famous Permian supercontinent, earlier giants such as Columbia, Rodinia, and later Gondwana had already gathered the planet's major landmasses into single, sprawling entities and then torn them apart again. When Rodinia formed more than 1 billion years ago, most of the planet's crust was welded into one broad equatorial block. During this time, mountain belts rose where continents collided, and interior regions lay far from the moderating influence of the oceans. Over time, that arrangement altered wind patterns, ocean circulation, and even the distribution of ice. As Rodinia eventually rifted apart, new ocean basins opened, and narrow seaways began to redirect currents in ways that would have been impossible on a scattered set of small continents. Each supercontinent layout imposed its own rules on climate. A single giant landmass tends to produce dry, seasonal interiors and strong temperature contrasts between coast and center. In contrast, many mid-sized continents separated by wide oceans favor more humid belts and smoother climate gradients. One way to picture this is to imagine a nearly closed ocean basin, ringed by land, where water circulates slowly and can become stagnant, versus an open global ocean with broad gateways that let currents sweep heat from the equator toward the poles. Because of this, simply shifting a continent by a few thousand kilometers can change rainfall patterns, storm tracks, and the locations of fertile coastal habitats. Supercontinent breakup added another layer to this process. When a large landmass began to stretch and fracture, the thinning crust subsided and allowed shallow seas to flood its edges. These broad continental shelves were bathed in sunlight and supplied with nutrients from rivers. As a result, they often became hotspots of biodiversity, filled with reefs, shell-bearing animals, and complex food webs. At the same time, they were unstable environments, sensitive to changes in sea level, chemistry, and temperature. What happened when those shallow seas suddenly warmed, lost oxygen, or retreated? Over Earth's long history, this cycle of assembly and breakup ran several times. Each iteration refined the links between mantle heat, plate motion, ocean circulation, and the rise and fall of life. Gondwana's gradual fragmentation, for example, did not just redraw coastlines, it altered deep water formation and helped set the stage for later greenhouse and icehouse phases. During this time, extinction pulses often coincided with rifting events, volcanic outpourings, and the reorganization of ocean gateways. Seen against this background, Pangaea was one more turn of a familiar tectonic wheel. Its assembly and breakup followed patterns first explored by Rodinia and other early supercontinents. The end Jurassic crisis fits into this larger story. It did not arrive as a single catastrophic blow from space. Instead, it emerged quietly during one of these breakup phases, as new oceans opened, seaways narrowed, and environmental stress accumulated in those once prosperous shallow seas. To understand why the Jurassic world faded rather than exploded, the next step is to follow Pangaea into its rifted, leaking stage and watch how that slow tectonic experiment reshaped climate, oceans, and life. To see why this quiet extinction unfolded, the story has to move beneath the oceans and continents, down into the slow machinery of the planet itself. Long before any sudden crisis appears in the fossil record, Earth's interior is already setting the conditions for future collapse. Plate tectonics is the name given to this hidden engine. The planet's outer shell, called the lithosphere, is broken into rigid plates of crust and uppermost mantle. These plates do not sit still. They float and slide on the softer, slowly convecting mantle beneath, where rising and sinking currents of solid rock move over time like an extremely sluggish fluid. New oceanic crust is formed at mid-ocean ridges, where upwelling mantle melts and spreads outward, while old crust is driven back into the interior at subduction zones. As these plates migrate, they constantly rebuild the face of the planet. When plates diverge, they open new ocean basins and lengthen mid-ocean ridges. When they converge, they crumple crust into mountain belts, close ancient oceans, and weld continents together. Transform boundaries slice the surface sideways, shifting entire regions relative to one another. Because of this continuous motion, seaways open and close, coastlines migrate, and the positions of continents with respect to the poles and equator keep changing. Each of these shifts alters winds, ocean currents, and the distribution of habitats. This process does more than rearrange geography. It also drives long chains of cause and effect that link the deep mantle to climate and life. At spreading ridges and volcanic provinces, magma rises and releases large amounts of carbon dioxide into the atmosphere. As a result, periods of rapid seafloor spreading often coincide with higher background CO2 and warmer global climates. Warmer conditions can accelerate chemical weathering of continental rocks, change rainfall patterns, and influence how much sediment and nutrients rivers carry to the sea. These climate changes feed back into the oceans. When temperatures rise and sea levels respond, shallow continental seas can expand or shrink, reshaping the broad sunlit shelves where many marine organisms live. Warmer surface waters and altered circulation can reduce the supply of oxygen to deeper layers. Over time, parts of the ocean may become dysoxic or anoxic, turning into stressed or even deadly environments for many species. In the rock record, these intervals often appear as dark, organic-rich shales that mark past oxygen-poor conditions. Geologists think in terms of these process outcome loops. A modest increase in volcanism can change CO2 levels, which shifts climate, which modifies weathering, which alters nutrient delivery and ocean chemistry, which then feeds back into biological communities. Such loops can amplify slowly, turning an initially small tectonic adjustment into a large environmental transformation. Could a gradual change in ridge length or subduction geometry really help to end an entire geological period? During this time at the end of the Jurassic, several of these loops were quietly reinforcing one another. Pangaea was rifting, new seafloor was spreading in the nascent Atlantic, and large volcanic systems were releasing greenhouse gases. Sea levels fluctuated, circulation patterns reorganized, and signs of expanding ocean anoxia began to appear. The stage was being set for a tipping point, and the next step is to examine how these converging forces actually played out in Jurassic seas and skies. By the time the late Jurassic oceans began to falter, the deep cause had been building for hundreds of millions of years. To understand why the end Jurassic crisis unfolded the way it did, it is necessary to go back to the long assembly of Pangaea itself. During the late Paleozoic era, roughly 335 to 250 million years ago, Earth had a very different arrangement of land and sea. Separate continental blocks drifted slowly across the planet, carried by moving plates in the upper mantle. Over time, these scattered fragments converged and collided. This process did not happen in a single event. It unfolded through a sequence of major collisions that gradually locked the continents into one vast landmass, Pangaea. One of the most important stages was the suturing of Laurasia in the north with Gondwana in the south. When these large continental masses met, their buoyant crust could not easily sink. Instead, the edges crumpled, thickened, and rose. As a result, long mountain belts formed where oceans once lay. The collision that helped close the Reek Ocean contributed to the Appalachian Mountains in what is now eastern North America, while farther north and east, the meeting of different continental blocks raised the Ural Mountains between what would become Europe and Asia. During this time, subduction zones consumed wide tracts of oceanic crust. Ocean basins narrowed, island arcs were swept into continental margins, and smaller microcontinents became welded onto larger plates. Because of this repeated accretion, the margins of the growing supercontinent were stitched together by complex sutures. These zones contained thick piles of deformed rock, remnants of ancient seafloor, and deep-rooted faults that extended far into the lithosphere. The environmental consequences of supercontinent assembly were profound. When most of Earth's land fused into one body, total coastline length dropped sharply. There were fewer broad, shallow continental seas, and more of the planet's surface water occupied deep ocean basins. The interior of Pangaea lay far from any moderating ocean influence. Summers became hotter, winters colder, and large regions experienced strong seasonal drought. Over time, this produced vast deserts and stressed ecosystems that had once relied on humid coastal climates. At the same time, the joined continent altered how heat moved within the mantle. Insulating crust above a broad area reduced the efficiency of heat loss. Mantle material slowly warmed beneath Pangaea's interior, while the thickened roots of its mountain belts stored mechanical stress. In a sense, the supercontinent acted as a lid, allowing thermal and tectonic potential energy to accumulate beneath and within it. Those ancient sutures and weakened zones would not remain quiet. As mantle heat built and plate motions changed direction, extension began to replace compression. The same belts that had once been crumpled were pulled apart. Rifts opened along old collision zones. Magma rose through inherited faults, and new ocean basins started to form. By the late Jurassic, these reactivated weaknesses had become the rift systems and volcanic centers that would help drive environmental instability, setting the stage for the quiet extinction that followed. By the time those late Jurassic rifts were spreading and magma was welling up along inherited faults, the world above them was dominated by a single, extraordinary continent. Pangaea stretched almost from pole to pole, a continuous expanse of land that gathered nearly all of Earth's major crustal blocks into one connected mass. Around it lay the global Panthalassa Ocean, with the narrower Tethys Ocean cutting into its eastern side like a long, tropical inlet. On a modern map, this supercontinent would look unsettling. Instead of scattered continents separated by wide oceans, there was one giant body of land ringed by a single, endless shoreline. Mountain belts traced the scars of earlier collisions through its interior. Broad lowlands sloped toward Panthalassa and Tethys. During this time, distances across Pangaea were so great that a journey from the interior to the nearest coast could span thousands of kilometers, crossing deserts, upland plateaus, and seasonal river systems. Such an arrangement profoundly altered climate. Oceans act as vast heat reservoirs, but on Pangaea, most of the land surface lay far from their moderating influence. Summers in the continental interior were intensely hot and dry, while winters could become surprisingly cold. Along the margins, moist air from Panthalassa and Tethys fueled powerful monsoon systems. Seasonal winds shifted, drawing in warm, water-laden air that rose over the land and dropped heavy rains, then reversing to send dry air back toward the sea. As a result, Pangaea experienced climate contrasts that were sharper than those on the planet today. Coastal belts endured alternating wet and dry seasons, with swollen rivers and broad floodplains during the monsoon, followed by months of retreating waters. Farther inland, high-pressure cells favored clear skies and evaporation. Hyper-arid deserts spread across central regions, leaving dune fields and evaporate deposits that still record this process in the rock record. Life adapted to these extremes in distinct ways. In the interiors, only hardy plants could survive long dry intervals, including drought-tolerant conifers and seed ferns with deep roots and tough leaves. Along the coasts and river plains, lush wetlands formed supporting horsetails, ginkgos, and dense conifer forests. Early reptiles and synapsids exploited this mosaic of habitats, evolving thick skins, efficient lungs, and water-conserving physiologies that made them well-suited to hot, variable conditions. Yet the very scale of Pangaea imposed limits. With coastlines compressed into a single perimeter and vast interiors dominated by similar arid climates, habitat diversity was lower than on a world with many separate continents. Because of this, ecosystems could be sensitive to relatively small shifts in sea level or rainfall. A modest change in monsoon strength, or a slight flooding of low coastal regions, could reorganize entire biomes over time. Beneath this apparently stable supercontinent, tectonic forces were already pulling it apart. Rifts lengthened, volcanic centers intensified, and shallow seaways began to probe into the continental mass. These first cracks in Pangaea would not only rearrange the continents, they would also start to alter ocean circulation, oxygen levels, and climate in ways that would quietly undermine Jurassic ecosystems. How did those hidden changes in the oceans turn a stable world into one on the brink of extinction? By the late Triassic and early Jurassic, the quiet rearrangement of ocean circulation had a very direct cause. The supercontinent itself was beginning to break. Along what would one day become the margins of North America, Africa, and Europe, the rigid crust started to stretch, thin, and fracture. Instead of a single unbroken landmass, Pangaea entered a long phase of mechanical failure that would reshape the planet's surface. During this time, great linear depressions opened as the crust sagged between sets of faults. These rift basins, such as those now preserved along the eastern margin of North America and in northwestern Africa, filled with rivers, lakes, and thick piles of sediment. At first, they were simply long, low valleys. Over time, they became channels that would guide in future oceans. This process recorded, in rock, the first clear signs that Pangaea's stability was ending. As the stretching continued, magma from the mantle exploited the weaknesses. Huge volumes of basaltic lava erupted along the developing rift zones, covering wide areas in stacked flows. Together, these eruptions formed one of the largest volcanic provinces in Earth's history, the Central Atlantic Magmatic Province. It spread across what are now eastern North America, northern South America, northwest Africa, and western Europe, a vast frozen imprint of mantle heat reaching the surface. Because of this, the early Atlantic region was not yet an ocean, but a landscape of fissures, lava plateaus, and subsiding basins. These geological changes had profound biological consequences. As the crust separated and subsided, narrow seaways and shallow epicontinental seas began to form between once adjacent continents. New coastlines appeared, with deltas, lagoons, and broad continental shelves. Such environments created a mosaic of habitats for marine invertebrates, coastal plants, and early marine reptiles. As a result, local biodiversity often increased as organisms exploited fresh ecological space and new migration routes along these young margins. Yet this apparent gain carried a hidden cost. The same rifts that generated new habitats also fragmented once continuous ecosystems. Populations of ammonites, bivalves, and coastal vertebrates that had once ranged widely across Pangaea found themselves separated by expanding seas and shifting land barriers. Isolation encouraged endemism, with distinct faunas evolving in different basins. This made regional communities more unique, but also more vulnerable when environmental stress struck particular ocean gateways or shelves. Here, a pattern interrupt appears in Earth's history. The breakup that seemed to energize life was also quietly setting up future crises. By the middle and late Jurassic, the Atlantic was no longer a mere chain of lakes and rifts. It was a growing ocean, flanked by complex continental outlines. Ocean currents, climate belts and migration pathways were all being rewired. When the end Jurassic extinction unfolded, it did so on a planet already in mid-transformation, with continents parting, volcanic provinces established, and ecosystems divided into a patchwork that would respond unevenly to the next wave of environmental change. By the middle to late Jurassic, that patchwork planet had settled into a surprisingly stable pattern. Millions of years before the quiet crisis at its end, Earth carried a version of Jurassic World that felt enduring and secure. What did this world look like, and why did life flourish so strongly under these conditions? At this time, Pangaea was no longer a single unbroken landmass. The supercontinent had begun to tear, and broad rift systems had opened between the blocks that would later become the modern continents. A narrow, elongating proto-Atlantic occupied these rifts, widening slowly between what are now North America, Africa, and Europe. Around the margins of these separating continents, shallow epicontinental seas flooded low-lying crust. These broad, sunlit shelves formed a vast coastal realm that wrapped around much of the planet. The global climate during this time was a greenhouse state. High levels of atmospheric carbon dioxide and strong internal heat from the mantle meant there were no permanent ice caps at the poles. Temperature gradients between equator and high latitudes were gentle, and warm waters could move easily across the surface. Because of this, sea level remained high, and shallow seas extended far into the interiors of continents, creating long, intricate coastlines and semi-enclosed basins. Ocean circulation followed this geography. The Great Tethys Ocean stretched across the low latitudes, linking the eastern and western hemispheres, while the developing Atlantic opened as a narrow seaway to the north and west. Currents could pass between Tethys and the young Atlantic, carrying heat, nutrients, and organisms. This process created broad belts of upwelling and mixing that fertilized surface waters. As a result, many marine regions supported dense plankton blooms, which in turn fed complex food webs from the seafloor to the top predators. Marine biodiversity reached a high point under these conditions. Ammonites with tightly coiled shells and belemnites with bullet-shaped internal guards filled many ecological roles in the open water. Reef-building corals and sponges constructed extensive carbonate platforms along the edges of continents and on isolated highs in the shallow seas. Above and around these reefs hunted large marine reptiles. Pliosaurs with massive heads and powerful jaws, long-bodied plesiosaurs, and streamlined ichthyosaurs dominated many top predator niches, tracking schools of fish and cephalopods through clear, warm seas. On land, equally distinctive Jurassic ecosystems developed. Vast conifer forests, joined by cycads and ginkgos, covered much of the continental interiors, with thick fern undergrowth filling the shaded floor. In these landscapes, sauropod dinosaurs moved in herds, feeding on high branches and leaving extensive trackways in floodplain sediments. Stegosaurs browsed lower vegetation, while early theropods patrolled as active carnivores. Warm, humid conditions, with relatively mild seasonal contrasts, allowed year-round growth in many regions. This was the control state for the end Jurassic story, a flourishing greenhouse world, supported by stable circulation and extensive shallow seas. Over time, however, small shifts in sea level, volcanic gas release, and ocean chemistry would begin to test this system. How would these seemingly modest changes undermine such a successful arrangement of life? The answer lies in how sensitive this interconnected Jurassic world really was. To understand how that sensitivity was tested, the story must move from the land to the oceans. During this time, the breakup of Pangaea did not just rearrange the continents, it quietly rewired the circulation of the entire global ocean. As plates shifted and rifted apart, narrow seaways opened, widened, or closed, redirecting currents that had once flowed more freely across the planet. Millions of years earlier, much of the Panthalassic Ocean behaved like a broad, open basin. Water masses could travel long distances, carrying heat, salt, and nutrients between different regions. Over time, however, rifting between what would become North America, Africa, and Europe produced a more complex pattern of semi-enclosed basins and gateways. Instead of one vast, well-connected ocean, the late Jurassic seas began to resemble a maze of compartments, each with its own circulation quirks. This change can be imagined in simple terms. A wide, open ocean allows surface and deep waters to mix more easily, preventing strong stratification. In contrast, a chain of restricted basins connected by shallow or narrow passages tends to trap water. Exchange with the open ocean slows. When warm, salty surface waters become stable over cooler deep waters, vertical mixing weakens. As a result, oxygen from the atmosphere has a harder time reaching the seafloor, and deeper layers can become stagnant. Geological records show that this process was not just theoretical. Sediment cores and rock layers spanning the late Jurassic-early Cretaceous transition preserve clear signs of changing water temperature and chemistry. Oxygen isotope measurements from carbonate shells indicate shifts in seawater temperature patterns, suggesting that currents transporting heat were being reorganized. At the same time, carbon isotope curves record disturbances in the global carbon cycle, pointing to intervals when organic matter burial and ocean ventilation changed together. In several regions, dark, organic-rich shales appear within successions that had previously been dominated by lighter, well-oxygenated sediments. These black layers often contain pyrite and show limited evidence of burrowing by seafloor organisms, a combination that signals low oxygen or even anoxic bottom waters. Because of this, geologists interpret them as episodes when restricted circulation and stratification allowed oxygen to be consumed faster than it could be replaced. Biologically, the consequences were significant. Areas that had once supported thriving reef systems and dense ammonite communities began to experience periodic or chronic oxygen shortages. Reef-building organisms declined in some basins as stressed waters favored more tolerant, opportunistic forms. Ammonites and other nectonic animals faced shifting habitat boundaries as oxygenated zones contracted vertically and horizontally. How could such gradual changes in currents and chemistry undermine whole ecosystems? The answer lies in the cumulative effect. Gateways that seemed minor on a map controlled how deep waters formed, where nutrients upwelled, and which shelves remained ventilated. In certain late Jurassic and earliest Cretaceous basins, the oceans were not simply warming. They were, in places, starting to suffocate. The quiet crisis in circulation had begun, but the most severe biological responses to these suffocating seas were still to come. In the background of this quiet oceanic crisis, another force was reshaping the planet from below. During this time, the late Jurassic was not marked by a single gigantic lava province, like the later Deccan traps, but by widespread volcanism linked to the slow unzipping of continents. As Pangaea continued to fragment, rifts opened, new ocean basins began to form, and mantle heat rose toward the crust along long, linear zones. This rifting did more than rearrange coastlines. As the crust stretched and thinned, it fractured, allowing magma to ascend in dike swarms, seafloor spreading centers, and scattered volcanic fields. Early phases of large magmatic systems, such as the Karoo-Ferrar province, had already affected the southern hemisphere, and related mantle upwelling continued to supply melt. Over time, these repeated eruptions released large volumes of carbon dioxide, sulfur species, and water vapor into the atmosphere, even without producing a single dramatic volcanic event. Prolonged volcanic outgassing is a powerful climate engine. When magma degasses CO2 over millions of years, it strengthens the greenhouse effect, trapping more heat near Earth's surface and gradually raising global temperatures. This process can shift rainfall belts, intensify some monsoon systems, and dry others because of this redistribution of heat between equator and poles. Continental interiors that once supported humid forests may have experienced more seasonal drought, while coastal zones received heavier, more variable storms. Rocks from the late Jurassic early Cretaceous boundary preserve traces of these changes in their chemistry. In marine limestones and shales, geochemists detect carbon isotope excursions, small but persistent shifts in the ratio of heavy to light carbon. These excursions signal disturbances in the global carbon cycle, enhanced volcanic input, altered burial of organic carbon, or short greenhouse spikes superimposed on a warm background. As a result, the sedimentary record shows intervals where carbon reservoirs on the planet were being reorganized, even when fossils suggest only gradual ecological change. The warming itself had direct consequences for the oceans that were already struggling with circulation. As surface waters became warmer and, in many regions, fresher from intensified rainfall, they grew more buoyant relative to the cooler, saltier deep waters below. This increased density contrast made it harder for the ocean to mix. Stratified water columns limited the downward transport of oxygen and the upward return of nutrients, allowing deep basins to slip further toward oxygen-poor and, in some places, nearly anoxic conditions. At this point, it is tempting to think of this as a distant and unfamiliar world. Yet the underlying physics is strikingly recognizable. Slow volcanic emissions, changed atmospheric composition, enhanced greenhouse warming, and altered circulation patterns in the air and oceans. The difference is scale. Processes that now unfold over centuries operated then over millions of years. The late Jurassic climate did not flip in a human lifetime, but the same fundamental rules of carbon, heat, and water still govern the planet. These volcanic whispers from the mantle set the stage. The next question is how life responded as the climate and oceans crossed critical thresholds. Those volcanic whispers from the mantle did not only warm the air above the continents, they also changed something far less visible, but far more dangerous: the way the oceans could breathe. When large regions of the sea lose their oxygen, the result is called ocean anoxia. And during this time, it turned entire basins into silent, uninhabitable realms for most complex marine life. In simple terms, anoxia means that dissolved oxygen in seawater drops to very low levels or disappears entirely. Many animals that lived in late Jurassic seas, from small crustaceans to larger swimming reptiles, depended on a steady supply of oxygen delivered by circulating currents. When that circulation faltered, the deeper parts of the water column became deadly. Organisms that sank from the surface died and fell into these dark layers, but their remains did not fully break down, because the microbes that usually recycle organic material also need oxygen. Several linked processes helped create these low oxygen zones. As greenhouse gases from long-lived volcanism trapped more heat, surface waters in many regions became warmer and less dense. Warmer, fresher water tended to float above colder, saltier water, setting up strong stratification. This process acted like a lid, reducing vertical mixing between surface and deep layers. At the same time, changing positions of the continents and the opening seaways of the early Atlantic altered currents and restricted circulation in some semi-enclosed basins. Because of this, deep waters were not efficiently replenished with oxygen from the atmosphere. When stratification persisted, the deep ocean could remain oxygen-poor for long intervals. Organic particles snowed down from the sunlit surface, accumulated on the seafloor, and were only partially decomposed. Over time, thick blankets of fine mud rich in carbon built up. Later, as these sediments were buried and compacted within the crust, they formed a distinctive rock: black shale. Black shales are dark, often finely layered sedimentary rocks that record these suffocating conditions. Their color comes from abundant organic matter that escaped full decay, sometimes together with minerals that form only when oxygen is scarce. In the late Jurassic and early Cretaceous, such rocks formed in many places, including broad areas of what is now Europe, around the ancient Tethyan margins, and in parts of the young Atlantic. These layers are not isolated curiosities. They appear again and again in the stratigraphic record, marking repeated episodes when regional or even widespread anoxia stressed marine ecosystems. For scientists reading Earth's history, these black shales act as a physical memory of crisis. Geochemical measurements within them, such as carbon and sulfur isotopes, show disrupted cycles that match declines in marine biodiversity. They reveal intervals when the planet's oceans periodically slipped into low oxygen states as climate and circulation crossed critical thresholds. If the seas themselves were losing their breath, which organisms felt the impact first? Did free-swimming predators, bottom-dwelling communities, or planktonic producers suffer most? And which lineages managed to adapt, migrate, or escape into refuges as the anoxic zones expanded? If low oxygen was one problem, the chemistry of the water itself was another. During this time, the very ingredients that many marine organisms used to build their shells and skeletons began to shift in subtle but important ways. The marine carbonate system can be described in simple terms. When carbon dioxide from the atmosphere dissolves into seawater, it reacts with water to form carbonic acid, which then breaks apart into bicarbonate and carbonate ions. Organisms such as corals, mollusks, and many plankton take calcium and carbonate ions from this mixture to form calcium carbonate minerals. This process allows reefs, shells, and many seafloor structures to grow, and it controls how easily the oceans of Earth can preserve these hard parts in the rock record. However, the balance is delicate. When more carbon dioxide enters the ocean, more of it is converted into carbonic acid. Over time, this tends to reduce the concentration of carbonate ions and lower the saturation state for calcium carbonate minerals. As a result, it becomes harder for organisms to precipitate solid skeletons and easier for existing shells to dissolve, especially in deeper or colder waters where pressure and temperature already push the system toward undersaturation. Near the Jurassic-Cretaceous boundary, several forces combined to disturb this balance. Large volcanic provinces linked to the breakup of Pangaea released pulses of carbon dioxide and other gases from the mantle into the atmosphere. Changing seafloor topography and gateways altered ocean circulation, affecting how heat and dissolved carbon were distributed through the water column. Because of this, some basins experienced intervals when carbonate saturation dropped, even if the surface waters still appeared relatively stable. Geologists recognize these intervals as carbonate crises. In certain late Jurassic to early Cretaceous sections, thick, bright limestones give way to darker, clay-rich or silica-rich sediments with much less carbonate material. Reef complexes that had built large frameworks earlier in the Jurassic become patchier and show signs of stress, with more broken fragments, more encrusting organisms, and fewer robust, branching corals. In some regions, entire carbonate platforms drowned, replaced by deeper water deposits that record a very different style of ocean chemistry. The biological consequences were significant. Thinner shells in ammonites and other mollusks suggest that maintaining heavy armor became more difficult as carbonate ions declined. Weakened reefs provided less habitat for diverse invertebrate communities, and higher mortality among larvae and juveniles would have amplified the impact of each chemical downturn. Which lineages could persist in waters that made skeleton building more costly, and which faded as their protective shells lost effectiveness? Yet these crises did not simply erase life. They reshaped it. Groups better adapted to fluctuating chemistry, including some new types of planktonic calcifiers, began to expand in the early Cretaceous seas. As older reef builders and shell formers struggled, these emerging lineages quietly prepared to dominate the next chapter. The question is how this hidden restructuring of the carbonate world set the stage for the very different marine ecosystems that would soon appear. As the carbonate world reorganized in the oceans, It did so against a backdrop of extraordinary biological richness. The late Jurassic was not a quiet, empty interval. It was a peak moment, when many of the organisms that define popular images of this period reached their greatest diversity just before the decline that followed. In the seas, ammonites and belemnites dominated the invertebrate realm. Ammonites carried tightly coiled shells carved into ribs, spines, and complex suture patterns where the internal walls met the outer shell. These shapes were not mere decoration. They influenced buoyancy, swimming ability, and resistance to water pressure. Belemnites, by contrast, possessed internal bullet-shaped guards that stabilized their squid-like bodies. During this time, both groups evolved rapidly, with life cycles closely tied to water temperature, nutrient levels, and oxygen in the upper ocean. As a result, even subtle environmental shifts could alter which species thrived. Reef systems added further structure to the marine landscape. Scleractinian corals, already established after earlier reef crises, formed dense frameworks in shallow sunlit waters. Between and upon these coral skeletons lived sponges, encrusting organisms, and thin microbial mats that trapped sediments. Together, this process built three-dimensional habitats filled with crevices, ledges, and overhangs. Fish, crustaceans, and juvenile reptiles sheltered in these spaces. When such reef builders faltered, entire communities lost their physical foundation. What happens when the architecture of the sea itself begins to vanish? Above and around these reefs, large marine reptiles ruled the open water. Pliosaurs, with massive skulls and powerful short necks, acted as top predators, able to tackle large prey with crushing jaws. Ichthyosaurs, shaped like modern dolphins, were streamlined for speed and deep diving, chasing fast-moving fish and cephalopods. Long-necked plesiosaurs, bearing small heads on extended cervical spines, specialized in ambush and in picking off smaller organisms from schools or reef margins. Because of this partitioning of roles, the late Jurassic oceans supported a layered predatory network that seemed, at first glance, stable and enduring. On land, the pattern was just as striking. Giant sauropods such as diplodocids and brachiosaurids moved across floodplains and conifer forests, feeding high into the canopy or sweeping low vegetation with long necks and tails. Stegosaurs, with their plates and tail spikes, occupied more localized herbivorous niches, while basal ornithopods, small to medium bipedal plant eaters, darted between larger dinosaurs and along river margins. Early theropods, including allosaurids and other large carnivores, tracked these herds, shaping the structure of terrestrial ecosystems. Yet even in this apparent abundance, some lineages were already waning. Diplodocid sauropods show signs of decline by the latest Jurassic, and several stegosaur groups become rarer in younger rocks. Over time, the familiar cast that defines the classic Jurassic scene would thin out, replaced by newer clades that would rise in the Cretaceous. The emotional weight of the end Jurassic event lies here. Many of the iconic animals associated with this era did not survive to meet the later Cretaceous giants at all. The next step is to examine how this thriving world began to unravel, not with a single impact, but through a series of environmental changes that quietly removed these stars from the stage. The end of the Jurassic is usually imagined as a single fading curtain, but in geological terms, it is stitched from two separate chapters, the Tithonian and the Berriasian. Around 152 to 145 million years ago, during this time known as the Tithonian, the last part of the Jurassic system unfolded. Immediately after, from about 145 to 139 million years ago, the Berriasian formed the first slice of the Cretaceous. These names come from regional rock successions in Europe, yet they now anchor a global boundary in Earth's history. Geologists divide time in a nested way. Eons contain eras, eras contain periods, and periods are broken into smaller stages such as the Tithonian and Berriasian. Each stage is defined not by a single catastrophe, but by patterns in rocks and fossils that appear in many places on the planet. As a result, the Jurassic-Cretaceous boundary is not just a date. It is a level in the rock record where several independent signals begin to change. At the end of the Cretaceous, a razor-thin clay rich in iridium marks the asteroid impact almost everywhere it is preserved. Nothing so sharp exists at the Jurassic-Cretaceous transition. Instead, the boundary is often diffuse, spread out through meters of limestone, marl, or shale. In some basins, the key changes appear a little higher or lower than in others. Because of this, the boundary can be diachronous, meaning that the Jurassic ends at slightly different horizons from one region to another. This creates a practical problem. When does the extinction actually happen? In some marine sections of Europe, major fossil turnovers occur below the level chosen as the formal boundary. In other regions, similar turnovers lie above it. The Earth's crust was not recording a single instant, but a drawn-out interval during which climates shifted, seas deepened or shallowed, and habitats moved across the surface. To navigate this complexity, geologists rely heavily on index fossils. These are species that were widespread, evolved rapidly, and are easy to recognize. For the Tithonian Berriasian, ammonites play a central role. Their coiled shells appear layer after layer, with distinct species replacing one another over time. Certain ammonite lineages vanish near the proposed boundary, while new forms arise and spread. This process helps tie distant rock columns together, yet it also introduces confusion when ranges overlap or when local conditions delay the arrival of new species. In some sections, ammonite extinctions, shifts in tiny plankton, and subtle changes in carbon isotopes line up neatly. In others, each signal peaks at a different level. Was there one crisis, or several pulses blurred together by sedimentation and erosion? If a real extinction unfolded here, why does it resemble a long geological fade instead of a crisp line? The next step is to look beyond the boundary itself and examine the environmental forces that could stretch an extinction into a drawn-out transition. To understand whether that drawn-out transition hides a real extinction, scientists step back and count life itself. They turn the scattered fossil record into diversity curves, graphs that track how many species or genera are known at each slice of geological time. When these curves rise, they show intervals when ecosystems diversified. When they fall, they point to crises when more lineages disappeared than new ones formed. During this time at the end of the Jurassic, those curves for the oceans begin to bend in a troubling way. Through the late Tithonian, marine diversity appears to climb, reaching a peak in many datasets just before the Jurassic-Cretaceous boundary. Ammonites, belemnites, and reef-building organisms seem particularly rich. Then, across the boundary, the lines drop. In some regions, whole ammonite families vanish. Certain belemnite groups thin out sharply. Coral and sponge reefs that had formed complex carbonate structures give way to simpler communities or to sediments with far fewer fossils. At first glance, this looks like a clear biological crash. But is it? Diversity curves are only as reliable as the fossil record behind them. The number of species known from any interval depends on how much rock of that age is exposed at the surface, how often those rocks are visited and sampled, and how well shells, bones, and skeletons survived burial. Because of this, an apparent rise in diversity can simply reflect more accessible outcrops, while a drop can signal that key rock layers are missing or deeply buried. This problem, known as sampling bias, is particularly strong near the Jurassic-Cretaceous boundary. Erosion has removed sections in some basins. In others, the boundary lies offshore beneath the modern ocean floor. As a result, raw counts of species through time can mislead, blending genuine extinctions with gaps in preservation. To separate these effects, researchers apply statistical methods that try to standardize the record. One approach is subsampling. Instead of comparing every fossil ever collected from each interval, scientists repeatedly draw equal-sized samples, asking what diversity looks like if each timed slice has the same sampling effort. Another strategy is to standardize by rock volume or outcrop area, adjusting diversity to match how much sediment of a given age is actually available. This process does not remove every bias, but it reduces the influence of uneven collecting and preservation. Even after these corrections, many studies still recover a downturn at the end of the Jurassic. The peak in late Jurassic marine diversity softens, but it does not disappear. Ammonites and belemnites show a sustained loss of lineages. Reef organisms decline in both richness and ecological complexity. Over time, the curves suggest that extinction is outpacing origination across multiple groups. If the fossil record is imperfect, yet still points to a real decline, then some force on Earth must have been quietly removing species faster than new ones could evolve. What kind of environmental pressure can erode biodiversity for millions of years without leaving a single dramatic boundary line? To find that pressure, scientists turn from bones to chemistry. Instead of counting shells, they read tiny changes in the atoms locked inside those shells. In particular, they examine stable isotopes, different flavors of common elements, such as carbon and oxygen, that are built into limestones, fossil shells, and organic matter as they form on the seafloor. These isotopes behave in slightly different ways during physical and biological processes. As a result, the relative proportions of light and heavy isotopes become a kind of code for past environments. When ancient seawater changed, the shells of ammonites, belemnites, and microscopic plankton also changed. Over time, those shells were buried, turned into rock, and preserved a continuous record of conditions on Earth's surface during this time. Carbon isotopes are especially important for tracing the global carbon cycle. The ratio of the heavier isotope, carbon-13, to the lighter carbon-12 shifts when large amounts of carbon move between the atmosphere, oceans, and sediments. A rise in carbon-13 can signal increased burial of organic carbon in seafloor muds. A fall can point to large releases of isotopically light carbon, such as methane from seafloor reservoirs, massive volcanic emissions, or rapid oxidation of organic matter on land. Across the late Jurassic to early Cretaceous, many sections show repeated carbon isotope excursions, sharp departures from background values. In some marine successions, these swings coincide with black shales that indicate low oxygen conditions, suggesting that pulses of volcanism or methane release may have driven greenhouse warming, ocean stagnation, and changes in carbon burial. Because of this, the carbon curves are interpreted as evidence for a carbon cycle that was being disturbed again and again, rather than sitting in long-term balance. Oxygen isotopes add a second vital sign. The ratio of oxygen-18 to oxygen-16 in marine carbonates depends on seawater temperature and, on longer timescales, on how much water is locked up in ice. Warmer water tends to produce lower oxygen-18 values in shells. Although the late Jurassic-early Cretaceous interval predates the large polar ice sheets of much later Earth history, oxygen isotope records still show recognizable shifts that point to warming episodes and altered ocean circulation. Here, a pattern interrupt becomes useful. Instead of imagining these isotope curves as abstract graphs, they can be viewed like a monitor in a hospital room. Carbon isotopes are the patient's heart rate. Oxygen isotopes are the blood pressure. Through much of the Jurassic, the lines rise and fall within a stable range. Around the JK boundary, both begin to show worrying irregularities, with rapid spikes and drops appearing in multiple basins on different continents. These synchronized disturbances suggest that the end Jurassic world was not simply drifting into the Cretaceous. It was passing through a series of environmental shocks, each one stressing ecosystems already losing diversity. The next step is to connect these chemical signals to concrete drivers in the solid Earth. The opening oceans, shifting seaways, and deep mantle heat that powered large igneous provinces and long-term climatic change. Those environmental shocks become much more tangible when the focus shifts from abstract curves to a single group of organisms. Among the most striking victims at the end of the Jurassic were the ammonites. These coiled cephalopods had reached one of their greatest peaks of diversity in the late Tithonian seas, filling tropical shelves, deeper basins, and even higher latitude waters with intricate shells and complex life cycles. During this time, ammonites were not just decorative fossils in the making. They were active predators, hunting smaller invertebrates and plankton in the water column, and at the same time they were important prey for marine reptiles and large fish. In many marine ecosystems, energy moved through food webs by passing in and out of ammonite populations. As a result, changes in their diversity and abundance signal broader shifts in how Jurassic oceans functioned. The fossil record shows that this flourishing did not continue uninterrupted across the Jurassic-Cretaceous boundary. In several regions, many ammonite lineages vanish at or just above the formal boundary horizon, leaving only a reduced set of clades to carry on into the early Cretaceous. In the classic Tethyan sections of southern Europe, for example, richly ornamented late Jurassic genera give way to a narrower, more uniform ammonite fauna in the earliest Berriasian. Over time, this pattern appears in multiple basins, from the Proto-Atlantic margins to parts of the Panthalasan realm. This decline was not random. Shell morphology, life history, and habitat preferences likely controlled which ammonites were most vulnerable to the changing planet. Forms with very thin, highly ornamented shells may have been more sensitive to carbonate chemistry stress when the oceans experienced repeated carbon cycle disturbances. Species that spawned in surface waters above stratified, oxygen-poor shelves would have been at particular risk as anoxia spread across the seafloor. Because of this, deep-dwelling or more robustly calcified lineages sometimes persisted where delicate, fast-growing forms disappeared. In several well-studied rock successions, the transition is visible layer by layer. In the limestone and marl sequences of the Vacantian Basin in France, ammonite-rich beds packed with diverse shells are overlain by thinner, more monotonous layers, holding only a few hardy species. In parts of the Andean margin, thick Jurassic intervals dominated by ammonites and belemnites pass upward into black shales with sparse cephalopods, but increasing traces of low oxygen conditions. This process is not a single catastrophic break. It is a stepwise replacement of complex faunas by simpler stressed communities. The end result is a quiet but profound restructuring of marine life. Ammonites survive into the Cretaceous, yet the groups present are a filtered remnant of their Jurassic peak. What makes this especially significant is that ammonites were not alone. In the same intervals, certain marine reptiles, carbonate platform builders, and other invertebrate groups also show parallel declines. Why do these collapses rarely appear in popular narratives of Earth history? And what do they reveal about how the planet's interior and shifting continents can reset entire ecosystems without a single impact crater? Those parallel declines are written most clearly in one of the planet's most sensitive habitats, the reefs. During this time, late Jurassic seas in many regions were lined with intricate, three-dimensional reef systems. These were not simple coral mounds. They were layered constructions built by framework corals, robust sponges, and dense microbial communities that bound sediment into rigid walls and buttresses in warm, clear, shallow water along continental margins. In these settings, sunlight penetrated the surface, and carbonate minerals precipitated readily from seawater. Over time, this process built reef structures several tens of meters thick, forming true underwater cities with ledges, caves, and steep slopes. Small invertebrates lived in crevices, fish hunted along the edges, and larger marine reptiles cruised the outer slopes. The reefs acted as both barriers and nurseries, shaping currents and concentrating life along the edges of Jurassic continents. Across the Jurassic-Cretaceous boundary, however, the architecture of these systems began to change. In some basins, continuous thick reef successions give way to much thinner, patchy buildups. In others, there are distinct gaps in reef development, where carbonate platforms that once teemed with coral sponge frameworks are replaced by simpler carbonate sands or even muddier deposits. Because of this, geologists see a clear signal. The most complex reef builders were struggling. There is also a shift in the dominant organisms doing the construction. Traditional coral sponge frameworks decline in several regions and are replaced by more microbial-dominated mounds or by low-relief biostromes that lack strong vertical relief. As a result, the seafloor becomes flatter and less varied in key intervals. This is not the complete disappearance of reefs everywhere, but a widespread restructuring, with fewer tall, rigid edifices and more subdued carbonate factories. Reefs respond quickly to changes in carbonate chemistry, temperature, and nutrient levels. When volcanic activity, shifting ocean gateways, or rising greenhouse gases altered seawater chemistry, the organisms that precipitated calcium carbonate were often the first to record the stress. Slight drops in carbonate saturation, increases in nutrient input from the continents, or episodes of reduced oxygen could all make it harder for corals and sponges to maintain their skeletons. In this sense, reefs acted as early warning systems for broader marine environmental change during Earth's late Jurassic history. When these habitats thinned or simplified, the consequences spread through the food web. Loss of vertical relief reduced hiding places for small fish and invertebrates, which in turn affected the predators that depended on them. Nursery grounds shrank. Migration routes along reef fronts were disrupted. For marine reptiles and fast-swimming fish, entire hunting landscapes were rearranged as the three-dimensional maze of the seafloor sagged into gentler slopes and open shelves. If the very architecture of the seafloor was being redrawn at the end of the Jurassic, what did that mean for the apex predators that had evolved to dominate a different kind of ocean? At the very end of the Jurassic, the surface of the oceans was still busy, but the hierarchy beneath the waves was starting to shift. The most dramatic changes can be seen among the giants that once ruled these seas, the large marine reptiles that had evolved to dominate a very different kind of ocean structure. When the late Jurassic oceans are reconstructed, they contain an extraordinary combination of predators. Massive pliosaurs, such as Pliosaurus and Liopleurodon, carried skulls longer than a human is tall, with deep jaws and heavy teeth designed to seize large prey. Streamlined ichthyosaurs, shaped like modern tuna or dolphins, moved rapidly through the water column. Long-necked plesiosaurs, with small heads and many neck vertebrae, patrolled shallower platforms and basins. During this time, all three groups shared the same seaways, hunting among ammonite shoals, belemnite swarms, and reef-fringing fish communities. Fossil records from Europe, South America, and parts of the ancient Tethyan realm show that this balance did not survive unchanged across the Jurassic-Cretaceous boundary. Many of the largest pliosaurids decline sharply or disappear from the record near the Tithonian-Berriasian interval. Some classic genera do not reappear in younger Cretaceous strata, and their ecological role seems to contract before it vanishes. Certain ichthyosaur lineages also thin out, with diversity curves indicating a reduction in both body size range and species richness. Over time, the once crowded apex tier becomes more sparsely populated in many basins. Several drivers likely acted together to produce this pattern. As ammonites, belemnites, and reef-building organisms declined, the prey base for giant predators became less reliable. This process reduced the dense, layered food webs that had supported very large carnivores. At the same time, the breakup of Pangaea and the opening of new ocean gateways altered current systems and reconfigured continental shelves. Broad, three-dimensional reef fronts gave way in places to flatter, muddier seafloors. Because of this, habitats that had concentrated prey into predictable hunting grounds were replaced by more open, less structured environments. Emerging Cretaceous predators added another layer of pressure. Early mosasauroid lizards, advanced teleost fish, and new, more specialized plesiosaurs began to occupy niches once held by giant pliosaurids and older ichthyosaur forms. As a result, competition in mid-level and upper trophic positions intensified even as overall productivity and habitat complexity were being tested by anoxic events and carbonate crises recorded in the rocks. Apex predators are often among the first visible casualties when ecosystems lose energy or structural complexity. When the seafloor architecture simplified and prey communities fragmented, the largest specialists were the least able to adjust their foraging strategies and life histories. Their disappearance is therefore an early signal that the end Jurassic oceans were undergoing a profound, if quiet, reorganization. To see this more clearly, it helps to pause and compare two scenes. Imagine a late Jurassic sea, crowded with pliosaurs, fast ichthyosaurs, and dense ammonite banks spiraling above bright reefs. Now shift suddenly to an early Cretaceous shelf. The water still blue, but the giants fewer, the reefs patchier, the silhouettes smaller and more scattered. What is missing from that second image, and what rose to take their place, points directly toward the next stage of marine evolution after the Jurassic world faded. On land, the shift was quieter, but just as real. Imagine walking from a late Jurassic floodplain into an early Cretaceous valley and seeing the same broad kinds of dinosaurs, yet realizing that many of the familiar faces have gone. The age of dinosaurs continued, but the cast on the continents was being rewritten. Paleontologists do not see a single sharp extinction line for dinosaurs at the Jurassic-Cretaceous boundary. There is no layer where all large forms vanish at once. Instead, several Jurassic lineages simply thin out, contract in range, and then disappear from the record over a span of time. In some regions, classic plated stegosaurs become rare after the late Tithonian and are gone by the early Berriasian. Certain long-necked sauropod groups that once ranged widely across the continents are increasingly confined to particular basins before they fade entirely. During this time, other herbivores were expanding. Ornithopods, including early relatives of the later duck-billed dinosaurs, diversified into more sizes and ecological roles. In some basins, they replace stegosaurs as the dominant medium-sized plant eaters. This process did not erase sauropods, but it altered the balance of herbivore communities. Over time, the Cretaceous pattern of herds of bipedal or facultatively bipedal ornithopods grazing alongside more specialized titanosaurs begins to emerge from what had been a Jurassic world dominated by different sauropod clades and armored forms. Theropod predators also show signs of turnover. Large Jurassic allosauroids decline in several regions, while new lineages, including early coelurosaurs and relatives of later tyrannosaurs, become more common in the record. In some formations, these newcomers appear first as minor components, then grow in diversity and size. As a result, the top of the food web is gradually reorganized, even though large carnivorous dinosaurs still stalk the floodplains and coastal plains of the planet. Underlying these biological changes were shifting physical conditions on Earth. The breakup of Pangaea was opening new ocean basins and changing the positions of the continents. As rifts widened and new seaways formed, regional climates were adjusted by altered wind patterns, different ocean currents, and changing sea levels. Forest belts may have shifted, conifer and cycad-dominated landscapes giving way locally to new plant communities. Because of this, the migration routes and available habitats for large herbivores and their predators were reshaped, fragmenting some populations and connecting others. The terrestrial fossil record across this boundary is patchy, with different rock units preserving different slices of time and environment. This makes it harder to draw a single global curve of dinosaur diversity. Yet regional studies, from Europe to Asia and parts of Gondwana, repeatedly suggest significant faunal turnover, rather than simple continuity. The dinosaurs did not vanish at the end of the Jurassic, but the ecological framework in which they lived was quietly rebooted by a crisis most people have never heard of, setting the stage for a distinctly Cretaceous world on land. In the middle of this quiet reshaping of dinosaur life, a deeper question emerges. Did the end of the Jurassic truly count as an extinction event? In Earth history, the term mass extinction is not used lightly. It usually refers to a geologically rapid loss of a large percentage of species across many different environments within a relatively short slice of time. When paleontologists speak of the Big Five crises, they mean intervals where reefs, open ocean ecosystems, and land communities all collapsed together. This process often involved sharp breaks in the fossil record, distinctive chemical signals in the crust, and major shifts in climate. By that classic standard, the late Jurassic to early Cretaceous transition sits in a gray zone. It shows real stress, but not always the sudden global crash seen at the end Permian or end Cretaceous boundaries. During this time, marine biodiversity clearly declined. Ammonites, belemnites, and several groups of reef-building organisms suffered significant losses, especially in basins that recorded low oxygen conditions. However, the disappearances are spread over several million years. Some regions show steep drops, while others record more gradual change or partial survival. Because of this uneven pattern, some researchers argue that the end Jurassic does not match the textbook image of a single, synchronized catastrophe. Instead, a number of scientists describe a prolonged faunal turnover. As Pangaea continued to fragment and new ocean gateways opened, currents shifted, sea levels fluctuated, and climate belts moved across the continents. Over time, these tectonic changes altered habitats step by step. Species that had once enjoyed broad, stable ranges were squeezed, replaced, or forced into new niches. In this view, the boundary marks the culmination of ongoing environmental reorganization driven by plate motion and long-term volcanic outgassing, rather than one short, lethal pulse. Yet the story is not that simple. In several well-studied marine sections, clusters of extinctions occur close to the Jurassic-Cretaceous boundary, accompanied by disturbances in carbon and oxygen isotope records. Black shales point to episodes of ocean anoxia, and carbonate crises hint at stressed surface waters. On land, certain dinosaur and pterosaur lineages vanish in a relatively narrow interval. Could these patterns represent at least one concentrated crisis superimposed on the longer background of faunal turnover? As a result, the debate has shifted from asking whether there was a single event to examining how multiple pulses and trends combined. Some researchers emphasize the drawn-out nature of the losses, while others stress the evidence for sharper peaks of extinction pressure. Both perspectives agree on one point. By the early Cretaceous, the planet's biosphere did not look the same. Regardless of the final label, the cumulative effect was profound. Marine food webs were restructured, reef systems changed character, and terrestrial ecosystems reorganized around new dominant groups. The end Jurassic may not fit a simple category, but it acted as a major ecological reset that opened ecological space. The question now becomes, what forces in Earth's interior and oceans were powerful enough to drive this quiet yet far-reaching transformation of life at the planet's surface? To understand those forces, it helps to notice something that is not there. At the end of the Cretaceous, the rock record contains a dramatic, almost theatrical signal. A global iridium-rich layer, shocked minerals, glassy spherules, and the 180-kilometer-wide Chicxulub crater buried beneath Mexico's Yucatan. In a single horizon, Earth's history records an impact so intense that it reshaped climates, oceans, and ecosystems in a geological instant. At the Jurassic-Cretaceous boundary, no such singular marker appears. There is no globally recognized crater of the right age, no continuous layer of impact debris that can be traced from continent to continent. Local impact structures from around this time certainly exist, because the planet is constantly struck by asteroids and comets, but none matches the scale, timing, and worldwide reach required to explain the broad biotic changes seen at the end of the Jurassic. The surface seems to record many small blows rather than one decisive strike. Because of this, attention turns away from a single catastrophe and toward a suite of slower, long-lived processes. During this time, Pangaea had already begun to fragment. As plates shifted, new seafloor formed along spreading ridges, and ocean basins widened. Volcanic provinces, including prolonged magmatism related to systems such as the Karoo-Ferrar, released large volumes of heat and gases from the mantle to the atmosphere. This process altered greenhouse gas levels, influenced climate gradients, and helped drive fluctuations in sea level. Over time, changing ocean gateways and seafloor topography reorganized currents. In several basins, black shales and geochemical signals point to expanding zones of low oxygen or anoxic water. These oxygen-poor layers stressed marine reptiles, ammonites, belemnites, and reef-building communities that depended on well-ventilated shelves. Instead of one sudden shock, lineages faded, recovered locally, and then declined again as pulses of volcanism, sea level change, and ocean stagnation interacted. The extinction signal becomes a pattern of repeated strain rather than a single breaking point. This makes the end in Jurassic event harder to communicate and remember. Human memory tends to favor clear narratives. One asteroid, one crater, one bad day for dinosaurs. How does one picture a drawn-out combination of mantle-driven volcanism, shifting continents, seafloor spreading, sea level oscillations, and creeping anoxia? The processes are powerful, yet they work through feedbacks and thresholds that are less intuitive than an impact fireball. A different image helps. Instead of imagining a single explosive crash, the end Jurassic can be compared to a slow-motion multi-car pileup in thick fog. No single collision destroys the entire line, but each small impact pushes the system closer to failure. Cars slide, bump, and lock together until the highway is transformed. In the same way, overlapping geological and oceanographic changes gradually altered habitats until many Jurassic ecosystems could no longer function in their previous form. This perspective sets the stage for examining how those intertwined forces are recorded in rocks, fossils, and isotopes across the Jurassic-Cretaceous transition. As those overlapping forces reshaped currents and chemistry, the solid outline of the Jurassic world was also changing. Millions of years ago, Earth had a very different arrangement of land and oceans, and the end of the Jurassic was marked by shorelines that refused to stay in one place. Sea level did not rise or fall once, it pulsed. What happens when the planet's coasts are repeatedly redrawn? During this time, global sea level followed a complex pattern of transgressions and regressions. Long-term tectonic changes altered the volume of the ocean basins, while shorter climatic swings shifted how much water was locked in polar regions. Over time, this produced broad phases when seas advanced onto the continents, followed by intervals when they retreated. Rock sequences from Europe, South America, and Asia preserve stacked packages of shallow marine sediments separated by erosion surfaces, a clear record that coastlines were marching landward and then back again. When sea level rose, continental shelves were flooded. Wide areas of low-lying crust that had once been coastal plains or river deltas became shallow epicontinental seas. This process created new marine habitats bathed in sunlight, where carbonate platforms and reefs could form, and where ammonites and other invertebrates spread into newly connected basins. At the same time, however, rising water drowned established coastal ecosystems, shifted river mouths, and altered sedimentation patterns. Mud and sand were rerouted, changing how nutrients and organic matter were delivered to the sea floor. Regressions reversed the pattern. As sea level fell, broad shallow seas shrank, and large areas of seafloor were exposed as barren coastal flats. Isolated marine basins became cut off from open ocean circulation, especially in regions already restricted by the breakup of Pangaea and the opening of new ocean gateways. Because of this physical isolation, bottom waters in some basins stagnated. Oxygen was consumed faster than it was replenished, amplifying anoxia and promoting the deposition of dark, organic-rich shales that mark regional ecological crises. These moving shorelines left a direct imprint on Jurassic Cretaceous life. Reef systems that had flourished on stable, flooded shelves declined as repeated drowning and exposure interrupted reef growth and stressed the organisms that built them. Ammonite faunas, which once formed nearly continuous belts around the margins of continents, became fragmented. Some lineages disappeared from certain basins while surviving in others that remained better connected. In several regions, marine reptiles vanished from the rock record just after major regressions, suggesting that shrinking hunting grounds and deteriorating water quality pushed already stressed populations past recovery. As a result, habitat loss and fragmentation were not abstract trends. They were lived realities for organisms bound to particular depths, temperatures, and water chemistries. Shorelines advanced, retreated, and advanced again, forcing entire communities to move, adapt, or vanish. In many places, their only lasting record is a thin layer of sand, a band of limestone, or a smear of black shale, quietly noting the moment when a familiar Jurassic coastline ceased to exist. Those vanished shorelines were not isolated curiosities. They were symptoms of a planet whose very framework was coming apart. During this time, the supercontinent that had once unified much of Earth's land was dividing into separate worlds, and that physical separation quietly rewrote the rules of survival. When long rifts cut into Pangaea's crust, they did more than create dramatic valleys. They severed once continuous belts of coastal plains, shallow epicontinental seas, and reef-fringed platforms. As these rifts deepened and flooded, new oceans formed, and broad habitats that had stretched for thousands of kilometers were sliced into smaller, more isolated pieces. A carbonate shelf that had once supported a single connected community of ammonites, belemnites, and reef builders could become a chain of separated basins, each with its own circulation, chemistry, and ecological history. This fragmentation promoted endemism. Species that had once ranged widely across Pangaea's margins and interior seaways now found themselves confined to particular regions, trapped on geological islands of suitable conditions. Over time, lineages of marine reptiles, invertebrates, and even terrestrial plants and dinosaurs diverged, adapting to local climates, currents, and nutrient regimes. In the short term, this process could increase global diversity because different basins and continents held distinct faunas. Yet it also made those lineages more vulnerable. A disturbance that affected one restricted basin, one gulf, or one island arc could erase an entire branch of the tree of life, with no neighboring population left to recolonize. Shifting land bridges and opening seaways further altered the paths that organisms could use to move and mix. Connections between Laurasia in the north and Gondwana in the south narrowed, widened, and narrowed again as sea level and plate positions changed. Because of this, migration routes that once allowed animals to track their preferred temperatures or follow food sources across the supercontinent were broken into segments. Gene flow slowed or stopped. Populations that might once have escaped a warming belt of climate or a spreading dysoxic zone found themselves blocked by deep water, desert interiors, or new ocean gateways that funneled currents in unfamiliar directions. By the late Jurassic, many ecosystems were effectively living on islands of habitat, even when they sat on large continents. A shallow, semi-enclosed basin along the future Atlantic margin could experience oxygen loss while an adjacent open shelf remained relatively stable. A reef system perched on a restricted platform might face rapid warming or changes in carbonate saturation that a more connected reef could endure. Environmental stressors such as anoxia, greenhouse pulses, or brief sea level drops no longer had to be global to be devastating. They could act locally, but with intense, irreversible consequences for highly endemic communities. In this fragmented world, extinction did not need a single impact or a planet-wide catastrophe. It could proceed basin by basin, margin by margin, quietly pruning different groups in different regions. The stage was set for a crisis that would look subtle in global averages, yet feel catastrophic from within each isolated sea and continent. The question is, how did this patchwork planet turn that hidden vulnerability into a real, measurable extinction event? To turn that vulnerability into real losses, living organisms had only a limited set of responses. When environments shift, life tends to follow three main paths. Species can adapt in place through genetic and behavioral changes. They can migrate to regions that still match their tolerances. Or they can disappear, first from local habitats and, in some cases, from the planet entirely. During this time at the end of the Jurassic, all three outcomes were playing out in parallel. In the oceans, the options were defined by depth, distance, and physiology. As surface waters warmed and certain basins slipped toward anoxia, many marine organisms could shift their depth ranges, retreating into cooler, more oxygenated layers. Ammonites, belemnites, and plankton could alter where their larvae developed, or where adults spent most of the year. Along continental margins, communities could migrate along coastlines, tracking upwelling zones or more stable currents. Over time, some lineages also modified life histories, changing growth rates, reproductive timing, or shell composition in response to altered chemistry. However, this process had strict limits. Warm, low-oxygen water expanded both at the surface and at intermediate depths, squeezing the habitable window for organisms that required well-ventilated conditions. Because of this, species that were highly specialized for narrow temperature ranges, particular food sources, or specific carbonate saturation levels had far less room to maneuver. Coral-like reef builders, for example, could only shift so far before light levels, sediment loads, or chemistry made growth unsustainable. Once entire depth bands or shelf areas crossed key thresholds, local extinction followed. On land, the basic choices were similar, but the geography of the late Jurassic added its own constraints. Large dinosaurs, early birds, and small mammals could track shifting climate belts, moving poleward or toward coastal regions as interior areas became more seasonal or more arid. As rift systems opened and seaways advanced, some groups moved between landmasses while corridors remained open, following river systems, low passes, and broad floodplains. In this way, continents that had once been tightly linked still allowed limited biological exchange even as they drifted apart. Yet the pace and complexity of the changes created a moving target. Tectonic reorganization altered coastlines, while volcanism injected greenhouse gases, metals, and nutrients into air and water. Warming, anoxia, changes in ocean circulation, and shifts in vegetation did not arrive one at a time. They overlapped. As a result, many specialized lineages faced not a single challenge, but a cascade of shifting pressures that exceeded their adaptive capacity. Here, a pattern interrupt helps clarify the scale of the problem. Modern species are confronting rapid climate change, ocean warming, and habitat fragmentation driven by human activity. They can adapt, migrate, or vanish, but highways, cities, and fragmented forests now block many migration routes, in the same way that narrowing seaways, rising seas, and broken land bridges constrained Jurassic migrations. The planet's crust, mantle, and atmosphere are different today, but the decision tree for life remains strikingly similar. The late Jurassic crisis, then, was not just about who disappeared, but about who could still move or change fast enough. The next question is how these uneven responses show up in the rock record and what they reveal about the true scale of this quiet extinction. To see how that decision tree for life is recorded, the story has to move from abstract curves back to real cliffs and road cuts. Millions of years after Pangaea first began to break apart, quiet slopes in the Tethyan realm captured the end of the Jurassic in layer after layer of sediment. Today, those layers stand as some of the clearest windows into this hidden crisis. In the European Alps, in the Apennines of Italy, and across parts of the Middle East, the ancient Tethys Ocean once covered wide continental shelves. During this time, fine carbonate mud slowly settled through warm, clear water and formed thick successions of limestone. These successions now appear as pale, massive walls, packed with ammonites, belemnites, and tiny planktonic fossils that allow geologists to follow time almost bed by bed. The same general pattern repeats from Spain to Iran, providing a broad framework for comparison. Closer inspection shows that these walls are not uniform. Over time, many sections shift from light, well-oxygenated limestone into darker, organic-rich layers and even thin, black shales. This process reflects changes in the water column as deeper parts of the Tethyan basins became poorly ventilated and oxygen levels fell. Because of this, bottom-dwelling communities thin out or vanish, while fossils of organisms that preferred low oxygen conditions become more common. The rock color, the texture, and the fossil content all change together. Geochemists add a second, quieter layer of information. In these same Tethyan sections, measurements of carbon and oxygen isotopes reveal subtle but consistent shifts across the Jurassic-Cretaceous transition. Ratios of carbon isotopes hint at disturbances in the global carbon cycle, while oxygen isotopes track changes in seawater temperature and perhaps in ice volume. No single spike dominates the record. Instead, a series of small steps and wiggles appears, repeating from outcrop to outcrop. The strength of these sections comes from correlation. When the same turnover in ammonite species, the same decline in certain reef builders, and the same isotope inflections are found in the Alps, in the Middle East, and in distant ocean-drilled cores, a composite picture can be assembled. This picture links local environmental shifts on individual continental margins to broader changes in ocean circulation and climate across the planet. It shows how the breakup of continents and the reorganization of ocean gateways translated into real ecological stress. Even in these best-preserved records, the boundary is not drawn at a single dramatic layer of ash or an obvious impact horizon. Instead, the formal Jurassic-Cretaceous line usually rests on a negotiated combination of fossil turnover, isotope behavior, and sedimentary change. The rocks do not shout about an extinction. Yet from multiple corners of Earth, they whisper the same story: warming seas, spreading low oxygen zones, and a gradual rearrangement of life. The next step is to ask how that whispered signal extends beyond the Tethyan realm into polar oceans and continental interiors, and whether it still points to a global event. Those whispers are hard to hear for another reason as well. The end of the Jurassic sits in one of the most awkwardly preserved chapters of Earth's rock record. When scientists try to count extinctions through time, they first have to ask a simple question that often goes unnoticed. How much rock from each interval actually survives at the surface of the planet? In many regions, late Jurassic strata are thick, widespread, and well exposed, especially along famous cliff sections and coastal platforms. By contrast, early Cretaceous rocks can be thinner, more fragmented, or buried beneath younger sediments. Over time, erosion removes some layers, tectonic deformation tilts or folds others, and vegetation or urban development hides many outcrops. As a result, some slices of Earth's history are wrapped in abundant, accessible rock, while others are represented by narrow belts, scattered quarries, or cores drilled from deep below the surface. The Jurassic-Cretaceous boundary often lies in the most problematic part of that architecture. In many basins, it falls within transitional facies, where shallow marine limestones grade into deeper muds, or where continental sands pass into nearshore deposits. These zones can be poorly exposed, weathered, or covered, so the exact horizon that marks the boundary is difficult to trace. During this time, a single hillside may preserve beautiful Jurassic ammonites, then jump directly to younger Cretaceous beds with little visible transition in between. Because of this, collecting large continuous fossil datasets across the boundary becomes a major challenge. Gaps in exposure interrupt fossil ranges. Changes in rock type alter which organisms are likely to be preserved. A shift from carbonate platforms to deeper basins, for example, can remove shallow water reef builders from the record, even if those lineages still survived somewhere else on the planet. This process can mimic extinction, or hide it behind changes in sedimentary environment. Human choices add another layer of bias. For more than a century, paleontologists have concentrated effort on spectacular faunas and visually striking outcrops. The classic Jurassic dinosaur beds of North America, the richly fossiliferous Solnhofen limestones, or the late Cretaceous sites tied to the famous asteroid impact. Subtle boundary intervals with sparse fossils and difficult stratigraphy attracted fewer teams, fewer detailed surveys, and fewer funding campaigns. Over time, this meant that the most dramatic events in Earth's history appeared better documented, while quieter crises remained in the background. To work around these problems, researchers apply statistical approaches that attempt to separate genuine biological signals from sampling artifacts. Methods such as shareholder quorum subsampling, occurrence-based diversity estimates, and models that track rock volume and outcrop area alongside fossil counts all converge on the same pattern: an elevated rate of extinction and faunal turnover from the latest Jurassic into the earliest Cretaceous. Even after correcting for changes in rock availability and collection intensity, many marine groups show a real contraction in diversity, followed by the rise of new lineages. This raises an unsettling question. If current data and methods are still biased toward loud, catastrophic events, how many other quiet extinctions might be hiding in plain sight, buried in transitional rocks and overlooked quarries, waiting for a closer examination of the planet's most ambiguous boundaries? To find the answer, the narrative has to move forward in time. By the early Cretaceous, tens of millions of years after the end Jurassic crisis, the planet's surface no longer carried a Jurassic world in recovery. It carried something new that had formed on the survivors' terms. In the oceans, this change is especially clear. Early Cretaceous seas held fresh ammonite clades with different shell shapes, ornamentation, and life habits compared with their late Jurassic relatives. Belemnites, the squid-like cephalopods with internal guards, also shifted, with new lineages experimenting with size, distribution, and depth ranges. Reef ecosystems reorganized as older coral and sponge assemblages gave way to different combinations of rudist bivalves, corals, and microbial frameworks, depending on local conditions. Marine reptiles did not simply return to their former Jurassic configuration. Ichthyosaurs, plesiosaurs, and emerging groups like early pliosaurs and marine crocodiliforms occupied altered food webs and hunting grounds. Because of this, recovery was not a simple reset. Vacant niches left by extinct lineages were filled by new groups that had different physiologies, growth rates, and ecological strategies. Over time, this process shifted the baseline of marine ecosystems. Plankton communities changed, carbonate production moved into new hands, and predator-prey relationships rebalanced in ways that would have been unrecognizable to organisms from the earlier Jurassic seas. On land, the transformation was just as profound. More derived ornithopods, including early iguanodontians, expanded into a wider range of body sizes and feeding roles, turning herbivorous dinosaur communities into more complex, layered systems. Coelurosaurian theropods diversified into agile, feathered predators and omnivores, setting the stage for later lineages that would give rise to birds. During this time, the earliest flowering plants began to appear toward the later part of the early Cretaceous, at first as minor elements on floodplains and coastal lowlands. Even in small numbers, their new reproductive strategies started to alter how nutrients and energy moved through terrestrial ecosystems. At first glance, this might sound like a smooth upward climb from crisis to stability. It was not. Lingering intervals of oceanic anoxia continued to affect basins around the continents, periodically suffocating deep waters and stressing marine life. Ongoing rifting of the crust and the gradual opening of new ocean gateways changed currents, climate patterns, and sea levels. Volcanic activity linked to shifting plates released heat and greenhouse gases, creating pulses of environmental stress that interrupted recovery and forced repeated adjustments. Here, a pattern interrupt is essential. The early Cretaceous should not be seen as a straightforward sequel to the Jurassic, with familiar ecosystems returning for another episode. It functioned more like a soft reboot. The same planet, the same continents in motion, but with new rules, new cast members, and new vulnerabilities. The next stages of the story would test just how resilient this reconfigured biosphere really was. The early Cretaceous world did not emerge in isolation. It followed another crisis, one that is often overshadowed by a far more famous catastrophe at the end of the Cretaceous. To understand why the Jurassic ending matters, it helps to place it beside the dramatic boundary that erased the non-avian dinosaurs 66 million years ago. When the Cretaceous closed, Earth experienced one of the sharpest shocks in its history. A large asteroid struck the planet near what is now the Yucatan Peninsula. The impact excavated a vast crater, hurled molten crust and vaporized rock into the atmosphere, and triggered global firestorms as ejecta rained back onto the surface. Thick dust and aerosols wrapped the planet in darkness. Photosynthesis faltered, food webs collapsed from the base upward, and many organisms that depended on rich plant production vanished in a geological instant. As a result, the boundary is marked by a thin, distinctive layer enriched in iridium, shocked minerals, and soot that can be traced around the world. The end of the Jurassic, by contrast, left no single crater and no razor-sharp line. Instead of one violent day, the planet endured a drawn-out interval of environmental stress lasting several million years. During this time, rifting continents altered ocean gateways, volcanic provinces pulsed in multiple phases, and climate oscillated under shifting greenhouse conditions. Ocean circulation changed, oxygen levels in some basins dropped, and carbonate systems faltered. Because of this, the fossil record shows not a single break, but a staggered pattern: ammonites fading in one region, reef builders declining in another, and certain dinosaur groups quietly disappearing from particular landmasses. Both endings reshaped life on land and in the seas, yet they did so through very different tempos and mechanisms. The KPG event acted like a sudden blow, instantly removing large non-avian dinosaurs, many marine reptiles, ammonites, and numerous plankton groups. The End Jurassic event functioned more like a series of tightening constraints. This process tested lineages over long intervals, favoring organisms that could cope with fluctuating sea levels, episodic ocean anoxia, and reorganized habitats on fragmenting continents. In each case, survivors inherited a transformed stage, but the script had been rewritten in different ways. Comparing these two boundaries reveals something important about Earth's vulnerability. The planet can be pushed into crisis both by abrupt external shocks and by slow compounding pressures generated from within the crust and mantle. Which is more dangerous in the long term, a single devastating impact or many smaller stresses accumulating until ecosystems can no longer adjust? Understanding the quiet end of the Jurassic shows that not all global crises announce themselves with a bang. Some arrive as a whisper, spread across rock layers, waiting to be decoded. The next step is to see how scientists read that whisper in detail and what it suggests about future changes still unfolding on this planet. Those whispers in the rock record do not stand alone. They sit inside a much larger rhythm in Earth's history. The the long, slow breathing of the supercontinent cycle. Over hundreds of millions of years, the planet's moving plates repeatedly gather the continents into single vast landmasses and then tear them apart again. Geologists now recognize several of these ancient configurations. Long before Pangaea, there was an early supercontinent, often called Nuna or Columbia, assembled more than 1.7 billion years ago. Later, another great landmass, Rodinia, formed and then fragmented, helping to set the stage for the strange climates of the late Precambrian. Pannotia followed near the end of the Precambrian, giving way over time to the assembly of Pangaea in the late Paleozoic. Looking ahead, some models predict a future supercontinent, perhaps dubbed Amasia or Pangaea Ultima, that may form when the present oceans close and the scattered continents collide once more. Each of these cycles follows a broadly similar sequence. First, long chains of subduction zones pull continents together, building huge mountain belts where plates collide. This process thickens the crust, releases large amounts of heat into the shallow mantle, and welds former fragments into a single, continuous landmass. Then comes a relatively stable supercontinent phase. When most land is clustered, interior regions become dry and seasonal, and the surrounding global ocean circulates around the margins. Eventually, the same insulation that made the supercontinent stable helps to destabilize it. Heat trapped beneath the thickened lithosphere accumulates. Mantle plumes begin to rise, the crust stretches, and rifts open across the surface. During this time, large igneous provinces erupt, new ocean basins are born, and narrow seaways cut into the supercontinent. Because of this, climate patterns, ocean currents, and sea levels are all disrupted at once. Major environmental and evolutionary transitions often cluster around these breakup phases. When continents separate, shorelines lengthen, shallow seas spread, and ocean gateways rearrange circulation. Oxygen-poor waters can expand, carbonate systems can falter, and ecosystems that once flourished along stable continental margins are suddenly stressed. As a result, extinction spikes and rapid radiations tend to accompany the rifting and volcanism that mark the end of a supercontinent's life. The end Jurassic crisis fits into this pattern. Pangaea was in the process of fragmenting, with the central Atlantic already opened and further rifting reshaping the map. Volcanic provinces linked to this tectonic reorganization altered atmospheric gases, while changing ocean gateways likely helped drive episodes of anoxia and carbonate instability. In this sense, the quiet Jurassic extinction resembles earlier disturbances tied to Rodinia's breakup and foreshadows later events associated with Cretaceous plate rearrangements. If supercontinent breakup reliably stresses life, what might that mean for Earth's distant future? When a new supercontinent eventually forms, will its assembly or its disintegration pose the greater challenge for the planet's biosphere? The rocks recording Pangaea's fate and the muted extinction at the Jurassic's end may hold clues that reach far beyond the age of dinosaurs into worlds that have not yet formed. Those clues point back to a deeper pattern. The end of the Jurassic was not a random disturbance. It was one pass through a repeating loop that links the planet's interior to its biosphere. To see why this quiet extinction matters, it is necessary to return to the engines driving Earth from below. Deep in the mantle, slow convection cells rise and sink as heat escapes from the interior. Over time, this motion stretches and fractures the crust, allowing new seafloor to be formed at mid-ocean ridges, while old seafloor is pulled down at subduction zones. This process does not happen once. It repeats across Earth's history. As ridges lengthen, plates accelerate, and then slow again. At certain moments, such as the breakup of Pangaea, the entire system shifts into a faster, more vigorous mode. When seafloor spreading rates increase, the consequences ripple outward. Hotter, more buoyant oceanic crust rides higher in the water, raising global sea level and flooding continental margins. At the same time, long ridge systems and large igneous provinces release more volcanic gases, including carbon dioxide, into the atmosphere. As a result, the climate warms, polar ice retreats or disappears, and shallow epicontinental seas expand across the continents. Warmer water holds less oxygen. With broad flooded shelves and restricted basins, circulation can become sluggish. In these settings, organic matter sinks, decays, and strips oxygen from the deeper layers, creating anoxic or even euxinic zones. During this time, many ammonites, belemnites, and reef-building organisms lived exactly in those vulnerable habitats. Their decline across the Tithonian-Berriasian interval reflects not a single catastrophe, but years to millions of years of mounting environmental stress. At first glance, this sounds like a one-way slide into crisis, but another set of feedbacks slowly begins to turn. Higher atmospheric CO2 and warmer temperatures accelerate chemical weathering on land, as rainwater reacts with silicate minerals in the crust. Rivers then carry dissolved ions to the oceans, where they help form carbonate minerals that bury carbon on the seafloor. Enhanced organic productivity in certain regions also leads to more organic carbon burial in black shales. Because of this, CO2 is gradually drawn down, and the climate can cool again. Here is the pattern interrupt. Imagine these processes not as a simple chain, but as interlocking gears in a vast machine: mantle convection, seafloor spreading, subduction, large igneous province formation, weathering, and carbon burial each turn at different speeds. Most of the time, they mesh without major incident, yet every so often, their teeth line up just right, and the outcome is a prolonged ecological crisis. The end Jurassic represents one such alignment. Mantle heat promoted rifting and volcanism. Seafloor production and CO2 outgassing increased. Seas rose, basins stagnated, and anoxia spread. Feedbacks eventually steered the system back toward a new equilibrium, but only after Jurassic ecosystems had been thinned, rearranged, and selectively pruned. What happens when the same gears align under even more extreme conditions will be the focus of the next stage in Earth's history. Those same gears, however, do more than explain a single Jurassic crisis. They offer a direct, if unsettling, comparison to the present. Millions of years ago, Earth responded to gradual increases in volcanic CO2 with warmer climates, rising seas, and oxygen-poor oceans. Today, the planet is being pushed along similar physical pathways, but on a radically different timetable. In the late Jurassic, CO2 outgassing from long-lived volcanism rose over hundreds of thousands to millions of years. During this time, the climate system had time to distribute heat through the oceans and atmosphere, and feedbacks in the carbon cycle slowly adjusted. By contrast, modern atmospheric CO2 has surged in just 2 centuries, driven by the rapid combustion of fossil carbon that formed deep in the crust and mantle over geological ages. Because of this compressed timescale, many of the same feedbacks that once moderated change are now lagging far behind. Despite the difference in pace, the physics and chemistry are strikingly familiar. Greenhouse gas concentrations increase, more heat is trapped, and the surface and upper ocean warm. Stratification strengthens as warm, light water caps denser, cooler layers. As a result, deep waters receive less oxygen, low oxygen zones expand, and nutrients are redistributed in ways that stress marine food webs. This process was recorded in Jurassic black shales and isotope shifts. It is now tracked by modern oxygen measurements and satellite observations. Jurassic reefs and other calcifying organisms show another parallel. When CO2 levels rose, more of it dissolved into seawater, altering carbonate chemistry and making it harder for corals and shell-forming plankton to build skeletons. Reef communities thinned, reorganized, and, in some regions, collapsed. Over time, entire marine ecosystems were restructured, with ammonites, belemnites, and several reptile lineages fading from the record. The end-Jurassic interval demonstrates that even relatively slow, natural CO2-driven changes can drive selective extinctions and long-lasting ecological turnover. The modern experiment is different in one crucial way: rate. Current CO2 increases are proceeding far faster than typical background fluctuations in Earth's recent geological history. If Jurassic ecosystems were pruned and rearranged by changes spread across millions of years, what happens when similar pressures arrive in mere centuries? How much biological reorganization can occur before long-lived species, complex food webs, and reef systems simply cannot keep pace? Seen from this perspective, the quiet Jurassic extinction is less a distant curiosity and more a muted warning. It shows that the planet's climate and oceans can cross thresholds without any single dramatic impact or global firestorm. The rocks that record those black shales, stressed reefs, and vanishing lineages suggest that Earth's systems do respond and sometimes fail when pushed. The remaining question is how those same gears will turn when the push is far stronger and far faster than anything the Jurassic world ever experienced. To follow those failing gears inside Earth's climate system, scientists have to rebuild a world that vanished 145 million years ago. The end of the Jurassic is not just a date on a chart. It is a layered, fractured record, spread across continents, ocean basins, and mountain belts. Reconstructing this interval depends on a set of key tools that work together. Field stratigraphy maps the order and thickness of rock layers along cliffs and cores. Paleontology tracks which organisms appear, flourish, and disappear within those layers. Geochemistry measures subtle changes in elements and isotopes that reflect shifts in carbon cycling, temperature, and oxygen levels. Geochronology uses radiometric dating to anchor those patterns to absolute ages. Numerical climate and ocean models then test how changes in plate positions, volcanic heat, and atmospheric composition could have shaped the planet during this time. In practice, this process looks less like a single experiment and more like assembling a long, interrupted film reel. Teams measure stratigraphic sections bed by bed, logging every limestone, shale, and volcanic ash. Fossils from each level, from large ammonites to tiny planktonic microfossils, are cataloged and tied to particular horizons. At the same time, carbonate shells and organic matter are sampled for carbon and oxygen isotopes, producing curves that rise and fall as the global carbon cycle and ocean temperatures change. Because of this, the isotope curves can be lined up with fossil ranges and with radiometric ages from ash beds that formed when magma from the mantle erupted through the crust. Over time, a coherent timeline emerges: pulses of volcanic activity, shifts in ocean circulation, intervals of black shale deposition, and phases when ammonite diversity drops or reef builders retreat. Each new dated ash layer or newly described fossil zone tightens the sequence of events by hundreds of thousands of years. Biostratigraphy is central to this effort. Ammonites, with their fast evolution and wide geographic spread, serve as primary markers, dividing the late Jurassic and earliest Cretaceous into fine time slices. Microfossils such as calcareous nanofossils and foraminifera add even higher resolution, especially in deep marine sediments far from the continents. When the same ammonite species or the same abrupt change in microfossil assemblages appears in distant basins, those layers can be correlated, revealing which environmental shifts were truly synchronous across the planet. Despite this integrated approach, the picture is not simple or unanimous. Different sections show different intensities of extinction, and some isotope records appear out of step with others. Disagreements over whether the end Jurassic represents a sharp crisis or a drawn-out restructuring of ecosystems drive new field campaigns, improved radiometric techniques, and more sophisticated climate and ocean models. Yet even with these advances, major gaps remain. Key intervals are missing where erosion stripped away the record, and whole regions of the planet have never been sampled in detail. The next fossil bed, the next precisely dated ash, or the next model run could overturn current timelines and reveal that the end of the Jurassic unfolded in a way that is far stranger than the present evidence suggests. Even with these uncertainties, one feature of the end Jurassic stands out: how invisible it is in the public imagination. Popular stories about ancient life tend to leap from the familiar Jurassic world straight to the late Cretaceous, as if the planet simply faded to black and then reopened on Tyrannosaurus and Triceratops. In that jump, an entire interval of quiet but significant change is left off the screen. In films, games, and museum displays, the word Jurassic often acts as a shorthand label for all large dinosaurs. The next widely recognized scene is the asteroid impact that ends the Cretaceous. Between those two images, there is almost no space for the gradual reshaping of oceans, climates, and ecosystems that took place as the Jurassic gave way to the Cretaceous. During this time, early bird lineages diversified, marine food webs reorganized, and several dinosaur groups declined. Yet those transitions rarely appear as part of a continuous narrative. One reason is structural. A single asteroid impact offers a clear beginning, middle, and end. It can be drawn as a fireball, followed by darkness, followed by extinction. The end Jurassic, in contrast, reflects overlapping processes: changing sea levels, shifting ocean gateways as continents moved, pulses of volcanic heat, and progressive loss of habitats. This process is harder to compress into a single dramatic moment. Because of this, it resists the simple plot lines that dominate large-scale storytelling about Earth's history. This absence matters. When attention focuses only on loud, catastrophic endings, it can create the impression that the planet's history advanced through rare, sudden disasters, separated by long periods of stability. The end Jurassic suggests a different pattern. Over time, biodiversity can be redirected by persistent, moderate pressures that act together: altered circulation in the oceans, gradual greenhouse warming, and incremental changes in the chemistry of seawater. As a result, lineages can vanish not in a single night, but over millions of years of steady environmental stress. Imagining this interval as a film highlights what is usually missing. Instead of an impact, the central image would be shorelines slowly migrating as rift basins deepen, reefs thinning as carbonate producers struggle, and black shales accumulating in oxygen-poor seas. Viewers would watch familiar Jurassic predators hunt in ecosystems that feel slightly out of balance, then notice, scene by scene, that certain ammonites no longer appear and some marine reptiles are rare. The tension would come from a question: how much change can these communities absorb before they reorganize into a new Cretaceous world? Placing the Jurassic-Cretaceous boundary back into the public story of the planet restores this quieter mode of transition. It shows that major evolutionary turning points do not always announce themselves with a crater. Sometimes they form at the intersection of plate motion, climate drift, and ecological feedbacks that only reveal their full impact when viewed across deep time. The next step is to examine how life responded once that new Cretaceous framework was in place. Across the early Cretaceous, the quiet framework set up at the end of the Jurassic began to unfold into a new planetary geography. Millions of years ago, Earth had a very different arrangement of land and oceans, but the basic pattern of rifts and rising mid-ocean ridges was already in place. The breakup of Pangaea did not stop with the first narrow seaways. Instead, it continued to pull the continents apart and reorganize the global ocean system. During this time, the Atlantic Ocean shifted from a thin, elongated basin into a widening expanse of water. Seafloor spreading along the mid-Atlantic ridge created new oceanic crust, pushed the Americas away from Africa and Europe, and allowed more water to flood into the growing basin. As a result, coastlines lengthened, shallow continental shelves expanded, and new marine habitats formed along the edges of the separating continents. This process also helped redirect ocean currents, which began to circulate differently around the changing landmasses. Farther south, Gondwana fractured into recognizably modern fragments. Africa, South America, Antarctica, India, and Australia slowly separated as rifts opened and new ridges rose from the mantle. Over time, the South Atlantic widened, the Indian Ocean took shape, and gateways began to open between the Tethys realm and the developing southern oceans. These changes did not just redraw the map, they altered how heat and salt moved through the oceans, which in turn influenced climate on land. Because of this long tectonic reorganization, today's continental positions and coastlines are the endpoint of motions that began in the late Jurassic and early Cretaceous. The familiar outline of the Atlantic, the curved coasts of Brazil and West Africa, and the narrowing connection between Europe and Africa all descend from those early rifts. Even the Mediterranean region is a remnant of the once vast Tethys Ocean, trapped and compressed as Africa moved north and collided with Eurasia. Without that earlier seaway, would the present cluster of Mediterranean climates and biodiversity hotspots exist in the same way? Modern ocean circulation also carries a clear imprint of this ancient breakup. The Atlantic now hosts a major overturning circulation, in which warm surface waters move north and sink, helping to regulate climate across the northern hemisphere. That circulation depends on the orientation and depth of the Atlantic basin, conditions that were set when the first Jurassic rifts opened and continued to evolve as plates moved. Coral reefs, mangrove belts, and upwelling zones today occupy margins created or reshaped during that interval. In this sense, the end Jurassic crisis is not only an event in the fossil record, it is part of the deep backstory of the modern world map. The oceans that transport heat, the continents that host forests and cities, and the climatic gradients that guide modern ecosystems all reflect decisions made by Earth's interior. During that quiet transition, the next question is how life, once placed on this shifting stage, adapted to and exploited the new Cretaceous world it inherited. Placed on this new Cretaceous stage, life did not simply begin again from zero. The end Jurassic interval shows that ecosystems can be reshaped not only by sudden catastrophe, but by long, grinding pressure that wears them down. Instead of a single asteroid, the planet experienced repeated pulses of volcanic activity, shifting sea levels, and reorganized ocean circulation. Over time, this combination produced a quieter but still profound ecological break. This pattern matters for understanding extinction risk. It shows that chronic environmental stress can erode resilience long before any final collapse. During this time, reefs declined step by step, ammonite diversity sagged, and oxygen-poor waters expanded across continental shelves. Each change on its own might have seemed manageable. Together, they pushed marine communities toward thresholds where familiar food webs could no longer be maintained. The result was not a single day of disaster, but a drawn-out loss of ecological options. In modern terms, this is an example of tipping points. Gradual forcing, such as sustained greenhouse warming or steady changes in ocean chemistry, can drive systems toward invisible boundaries. When those boundaries are crossed, the response becomes rapid and difficult to reverse. At the end of the Jurassic, carbonate crises, anoxia, and altered ocean gateways combined to move the seas past such thresholds. Coral and sponge reefs gave way to muddier, simpler seafloors, and many marine reptiles and cephalopods vanished from the record. Because of this multi-causal and prolonged character, the end Jurassic may be a closer analog to many real-world crises than the more famous asteroid impact. Present-day climate change, biodiversity loss, and ocean deoxygenation are not arriving as a single blow. They are arriving as overlapping waves that interact. This process resembles the interplay of volcanic gases, changing circulation, and continental breakup that quietly restructured Jurassic ecosystems. The lesson is that complex stress histories can be just as dangerous as singular cataclysms. Another important feature of this interval is the presence of early warning signs. Long before the full turnover, there were sustained reef downturns, repeated black shale deposits marking anoxia, and diversity curves that bent downward rather than upward. These signals show that the system was losing resilience. Recovery from smaller disturbances became slower, and communities failed to re-establish their former complexity. In effect, the biosphere was telling a story of strain long before the most visible losses appeared. The question is, how closely these ancient whispers match the signals emerging from modern oceans and continents? Are today's declining coral reefs, expanding oxygen minimum zones, and shrinking ranges for many species the same kind of early warnings? The rocks at the Jurassic-Cretaceous boundary suggest that listening carefully can reveal when a living planet is approaching a critical threshold. In the next section, the focus turns to how Cretaceous life responded and to what those survivors might reveal about navigating a world that has already crossed a line. In order to understand how Cretaceous life responded, it helps to step back and see the full arc that led to this quiet crisis. Across Earth's long history, the end of the Jurassic was not an isolated accident. It was the latest chapter in a story that began when the planet first formed, and its deep interior started driving the motion of continents and oceans. During its earliest history, Earth's surface was shaped by intense heat rising from the mantle. A thin, unstable crust formed, broke, and reformed as impacts and internal heat kept the young planet restless. Over time, small fragments of continental crust began to survive. Oceans condensed around them, atmospheres changed, and simple life adapted to shifting conditions that were controlled again and again by moving plates and changing seaways. Much later, the supercontinent Pangaea gathered most of the continents into one vast landmass. This enormous continent contained wide interior deserts, long coastal margins, and extensive shallow seas. During this time, plate motions compressed mountain belts along its edges and stretched its interior, storing energy that would eventually pull Pangaea apart. As rifts opened, new ocean crust formed, and the first narrow versions of the Atlantic and other basins began to appear. By the late Jurassic, this process had advanced far enough that Earth's geography was being rewired. Volcanic provinces linked to the breakup, such as early phases of the Karoo-Ferrar magmatism, released large volumes of gases into the atmosphere. Greenhouse warming intensified, sea levels shifted, and new ocean gateways changed how water masses circulated. Because of this reorganization, some basins became stratified, with warm, oxygen-poor waters spreading over the seafloor. As a result, several environmental pressures converged at once. Warmer climates altered rainfall and erosion on the continents. Rising and falling seas flooded shelves and then withdrew, repeatedly disturbing coastal ecosystems. In many regions, bottom waters turned anoxic, and black shales rich in organic matter were deposited. Carbonate systems were stressed, making it harder for some organisms to build shells and skeletons. None of these changes alone produced a single global catastrophe, but together they created a prolonged interval of instability. Marine life recorded this drawn-out crisis in detail. Ammonites and belemnites, once highly diverse and widespread, declined through the Tithonian and into the earliest Cretaceous. Reef-building communities, including certain corals and sponges, suffered repeated setbacks as water chemistry and clarity changed. Large marine reptiles such as pliosaurs and some ichthyosaurs lost ground, and several dinosaur lineages on land faded from the record as environments that had supported them were reorganized. Ecosystems did not simply collapse, they were restructured, opening opportunities for new Cretaceous groups. For this reason, the end Jurassic interval is now seen as a major turning point, even though it lacks a single impact layer or global ash bed. Was it a classic mass extinction or a complex multi-step turnover? The answer depends on how diversity is measured, but the direction of change is clear. Lineages that had dominated Jurassic seas and coasts were replaced by new assemblages that would define the early Cretaceous world. Reconstructing such a quiet ending has required careful work. Geologists correlate thin boundary layers across continents, track isotope shifts that reveal changing carbon cycles, and build diversity curves from incomplete fossil records. Subtle changes in limestone, black shale, and sandstone have been combined to reveal a planet under long-term stress. This painstaking reconstruction sets the stage for the next part of the story: how the early Cretaceous biosphere adapted to a world already transformed, and what those survivors can teach about resilience on a dynamic planet. Those reconstructed curves do more than quantify loss. They invite a different way of seeing time. Instead of imagining the age of dinosaurs as a single, unbroken landscape stretching from early Jurassic forests to late Cretaceous plains, the end Jurassic crisis marks a hinge. On one side stands a classic Jurassic world. On the other, a reorganized Cretaceous planet built from what survived. When this interval is placed at the center of the mental map, the familiar museum sequence quietly changes. Long galleries often flow from Jurassic displays into Cretaceous halls, as if one continuous ecosystem simply aged. Yet the rocks indicate that a reset occurred between them. Marine reptiles shifted, ammonite families turned over, reef systems restructured, and several dinosaur lineages faded from the record. The corridor between those halls represents not just a change in names, but a boundary where Earth's biosphere and climate were reconfigured. During this time, the breakup of Pangaea was not simply pulling continents apart, it was choosing future arrangements. As the Atlantic Ocean widened and ocean gateways opened or closed, currents were redirected, heat was redistributed, and new coastlines formed. This process altered rainfall patterns on land, oxygen levels in the seas, and the geography of habitats available to surviving organisms. Over time, these quiet tectonic decisions guided which regions would become humid refuges, which would dry into deserts, and which continental shelves would nurture the new Cretaceous marine communities. Because of this, many features of the modern planet can be traced back to that understated boundary. The positions of today's continents, the long Atlantic margin of the Americas, and the stepwise evolution of ocean circulation all carry the imprint of late Jurassic to early Cretaceous plate motions and extinctions. The end Jurassic event did not erase life in a single moment, but it narrowed options and redirected evolutionary pathways, setting conditions that later framed the rise of iconic Cretaceous dinosaurs and flowering plants. Here, a simple mental exercise can act as a pattern interrupt. The next time the words Jurassic or Cretaceous appear in a documentary, in a museum, or in a textbook, imagine a thin, glowing line drawn between them. What vanished at that line? Which lineages crossed it and diversified, and which stopped there entirely? Treating that quiet boundary as a real dividing line turns an abstract time label into a specific ecological threshold. Paying attention to such boring boundaries changes how Earth's history is perceived. Many of the planet's most important transitions are not marked by single craters or global firestorms, but by gradual stresses that accumulate and then tip systems into new states. Recognizing the end Jurassic extinction as one of these turning points prepares the ground for the next step in the story, following the Cretaceous survivors as they assemble the worlds that feel more familiar in the fossil record. The end Jurassic extinction is not only a chapter in Earth's history, it is also a test of how attention is directed towards certain crises and away from others. In museums, documentaries, and popular books, the narrative often jumps from a thriving Jurassic world directly to spectacular Cretaceous icons. During this time, a quiet but important boundary is passed over with a single sentence, or not mentioned at all. Once this has been seen, it becomes difficult to ignore. Exhibition panels may highlight the end Permian catastrophe and the later asteroid that ended the Cretaceous, yet provide no clear marker for the Jurassic-Cretaceous boundary. General audience books may treat the Jurassic as a stable backdrop rather than a changing stage, Watching for this absence turns the next visit to a gallery or the next documentary into an active search. Where is the transition, and how is it described if it appears at all? There are accessible ways to move beyond these gaps. Large online paleontology databases allow the distribution of fossils to be traced across the Tithonian-Berriasian interval, showing which groups decline and which expand. Open access scientific papers present diversity curves, isotope records, and new radiometric ages that refine the timing of environmental change. Virtual field trips guide viewers along limestone cliffs and deep-sea cores that physically record this boundary, making it possible to follow the contact between Jurassic and Cretaceous layers from a computer screen. Engaging with these resources reveals that the story is not finished. Many questions remain open about how abrupt the biodiversity losses really were, how strongly they were linked to volcanic pulses, and how much of the apparent pattern is shaped by sampling bias. Over time, new fossil discoveries from underexplored regions, such as southern continents or deep marine basins, can fill critical gaps. Improved dating techniques, especially high-precision uranium-lead measurements, can tighten the timeline and show whether separate environmental disturbances actually formed a single prolonged crisis. Because of this, the end Jurassic extinction should be seen as an ongoing investigation rather than a closed case. This process of comparing rock layers, analyzing geochemical signals, and testing different models for climate and ocean circulation depends on continuous re-examination. Viewers of this material are not limited to being passive observers of a completed narrative. By noticing what is emphasized, what is uncertain, and what is missing, each person becomes part of the broader analytical framework that shapes how Earth's past is understood. Seen in this way, the Jurassic-Cretaceous boundary becomes a lens for thinking about attention itself. If a crisis that reshaped marine ecosystems, altered dinosaur lineages, and accompanied the further breakup of continents can almost disappear from public awareness, what else might be overlooked? The final step is to carry that question forward, from ancient rock layers into present discussions of environmental change, and to ask, if a transition this significant can fade into the background, what other turning points in Earth's past and present remain hidden in plain sight? If a turning point as large as the end Jurassic can fade into the background, it suggests that Earth's history holds many more quiet boundaries that rarely enter public discussion. The close of the Jurassic is not the only moment when the planet shifted course without a single dramatic impact or a famous disaster. It is one chapter in a longer sequence of subtle transitions that, over time, have redirected the trajectory of life and climate. In this series, the goal is to place those chapters side by side, so that the end Jurassic sits next to other overlooked thresholds. Earlier episodes follow the assembly of Pangaea. When scattered continents collided, mountain belts rose, and the supercontinent formed as plates locked together. Later episodes examine how that same crust stretched and broke apart, opening new ocean basins and altering circulation patterns in ways that quietly transformed ecosystems. During this time, interior processes in the mantle guided the long arc of change. Future chapters will return to more familiar events, such as the end Cretaceous impact, but will set them within this broader macro timeline. The asteroid that closed the Mesozoic becomes one point on a continuum that also includes slower crises, like the end Permian or the more gradual cooling and ice growth that reshaped the Cenozoic. Because of this expanded view, individual extinctions are no longer isolated disasters. They become linked responses of the planet's surface, oceans, and atmosphere to deep-seated tectonic and volcanic drivers. Viewers are invited to stay connected to that unfolding story by subscribing and activating notifications, so each new boundary in Earth's history appears in order, from the early magma oceans to later supercontinent cycles and beyond. Upcoming episodes will revisit the first assembly of large cratons, the rise and breakup of earlier supercontinents before Pangaea, and the environmental oscillations that bracket the KPG event. This process of moving step by step through time makes it easier to see patterns that might otherwise be missed. Sharing this particular episode with others who are interested in dinosaurs, geology, or planetary change can help restore the missing chapter between popular Jurassic imagery and the familiar asteroid narrative. For many, the story jumps from lush Jurassic worlds directly to the end Cretaceous impact. The quiet restructuring that took place in between is rarely mentioned. Passing this along as that missing link encourages broader conversations about how continents, seas, and lineages actually evolved. Questions and observations from viewers form another important part of this project. Which aspects of the end Jurassic transition remain unclear? Which lesser-known extinction events, from regional reef collapses to shifts in Triassic faunas, deserve a full episode? Suggestions for future topics along the deep timeline help guide which intervals, isotope excursions, or tectonic reorganizations are examined next. Ultimately, the central idea is that subtle, slow-building extinctions are not minor footnotes. They are signals that the planet's internal and surface systems are being rewired. As a result, learning to read those signals in ancient rocks sharpens the ability to recognize comparable patterns in the present. Staying with the series and continuing the discussion beyond this episode keeps that long perspective in view as new chapters of Earth's story unfold.